Hello there, and welcome to Physics with William, where curiosity is allowed to slow down, complicated ideas are given a little breathing room, and physics is explored without any need to rush toward the answer. Tonight we are looking at something with a name that sounds almost suspiciously dramatic, the time crystal. It sounds like an object you might discover glowing in the corner of a laboratory after everyone else has gone home, or perhaps something a science fiction hero would hold up before announcing that history itself is about to change. Fortunately, the real thing is both less dangerous and more interesting. A time crystal cannot send you into the past, it cannot freeze a moment and keep it in a glass box, and it cannot tell you what you are doing next Thursday. What it can do is reveal a form of order that physicists did not seriously expect to find until fairly recently. A pattern that repeats not simply from one place to another, but through time itself. That is the strange idea we're going to settle into tonight. And before we begin properly, I would love to know where in the world you are listening from and what time it is for you right now. It feels especially fitting this evening, because somewhere it is early morning, somewhere else it is the middle of the afternoon, and somewhere a person is listening to a video about time crystals, while quietly hoping not to become too interested to fall asleep. If you find these slow journeys through physics calming, useful, or simply a pleasant way to end the day, I would be very grateful if you liked the video and subscribe to the channel. It helps this quiet little corner of science reach more people who might also enjoy discovering that the universe is much stranger than it first appears, provided we take our time with it. The phrase time crystal creates a problem almost immediately because both words give us very strong mental pictures and neither picture is quite right. When we hear crystal, we usually imagine something solid, transparent, angular, perhaps sparkling in the light. We think of quartz, diamonds, salt, snowflakes, or the sort of decorative object that somehow always looks more expensive when placed on a small velvet cushion. When we hear time, we imagine clocks, watches, calendars, appointments, birthdays, train schedules, and that peculiar way 5 minutes can feel very different depending on whether you're waiting for a kettle or already late for something. Put the words together and the mind naturally tries to create an object made from time, a little solid piece of the fourth dimension sitting politely on a table. Physics, however, is not using the word crystal in the everyday decorative sense. It is using the deeper idea behind crystals, the idea of repeating order. Once that becomes clear, the name begins to make more sense. An ordinary crystal is special because of the way its microscopic components are arranged. In a crystal of salt, for example, the atoms do not sit wherever they please. They form a regular repeating structure. If you could shrink yourself down far enough and move through the material, you would encounter the same arrangement again and again at regular distances. The crystal has a pattern in space. This repeating structure is one of the main reasons crystals have such recognizable properties. The important point is not that they sparkle or form attractive shapes. The important point is that their internal organization repeats. A time crystal takes that general concept and asks an unusual question. Could a physical system develop a repeating pattern not only across space, but across time? Could some measurable property of a system change, return, change again and return again with a regularity that is built into the collective behavior of the system itself? That is where the real idea begins. At first this may sound far too ordinary because plenty of things already repeat in time. A clock ticks, a pendulum swings, a heart beats, a planet circles a star. The drum in a washing machine rotates for an impressively long time whenever you're in a hurry. Repetition through time is not difficult to find. But these things are not automatically time crystals. A clock repeats because it has been constructed to do so, and because energy is supplied to keep it running. A pendulum swings because it has been set in motion, and if friction is allowed to do its work, the swing gradually disappears. A motor turns because electricity drives it. None of those examples captures the unusual physical idea that makes a time crystal interesting. To understand that, we need to think not merely about repetition, but about a physical system that organizes its response into a stable repeating pattern that is different from the rhythm being imposed upon it. Imagine a room full of people standing in rows. Every few seconds a bell rings. Whenever the bell rings, everyone turns around. One ring, one turn, another ring, another turn. The pattern is perfectly regular, but there is nothing surprising about it. The group is simply copying the timing of the bell. Now imagine the bell still rings at the same regular interval, but the people begin doing something different. Perhaps they return to the same overall arrangement only after every second ring. The bell gives one rhythm, while the group produces a larger repeating rhythm of its own. Even more interestingly, suppose the bell is not perfectly regular. Sometimes it is a little early, sometimes a little late, and sometimes someone presses the button slightly too hard because laboratory assistants, like everyone else, are human. Yet the group still manages to keep its own larger pattern stable. The behaviour belongs to the group as a whole, not to one person carefully counting. That rough picture gets us surprisingly close to the behaviour of what physicists call a discrete time crystal. The word discrete simply means that we are looking at the system at distinct repeated moments rather than treating every instant as identical. In many time crystal experiments, the system is driven by repeated pulses. Something is done to it again and again in a regular sequence. The simple expectation might be that the system responds with exactly the same timing as the driving pulses. Push it once, it responds once. Push it again, it responds again. Instead, under the right conditions, the system can settle into a different rhythm. It may return to the same measurable state only after 2 driving pulses rather than 1. The external drive repeats quickly, while the system responds with a slower repeated pattern. That difference is not just a curiosity. It is connected to a much deeper idea in physics called symmetry breaking, and that is where the word crystal earns its place. Symmetry in physics is not only about whether something looks balanced in a mirror, it is a broader idea describing situations where a change can be made without altering the essential physical rules. Imagine an empty room with a perfectly uniform floor. Before anything is placed in it, one location is no more special than another. The basic situation treats all positions in the same way. Now place a neat row of chairs across the room at regular intervals. Suddenly, some locations contain chairs and others do not. The underlying floor did not demand those particular positions, but the arrangement that formed has chosen them. A crystal does something similar. The laws governing the atoms do not mark out one tiny set of locations with invisible signs saying that atoms must sit here and nowhere else. Yet when the material forms crystal, the atoms organize into a repeating pattern that selects particular positions. The original symmetry of space has been reduced by the structure that appears. A time crystal applies an analogous idea to time. In a repeatedly driven system, each cycle of the drive may be physically equivalent. The driving process comes back again and again with the same timing, yet the system can respond in a way that distinguishes between those cycles. Instead of looking identical after every pulse, it may look identical only after every second pulse. The system has created a larger pattern in time than the one given to it. This is described as breaking a time translation symmetry. The phrase sounds formidable, but the basic idea is manageable. The rules repeat after a certain interval, while the actual state of the system repeats after a longer interval. The system has chosen its own pattern within the repeated timing of the drive. This is already different from a normal clock. A clock does not surprise us by following the mechanism we built into it. The gears, electronics, or vibrating components are deliberately designed to provide a particular period. A time crystal is interesting because the repeating behaviour appears as an organised property of a many-particle system. The phrase many-particle is important because time crystals are not usually about one isolated quantum object doing a clever trick. They arise from the interactions among many components. Those components influence one another, and together they can produce behaviour that is much more stable and structured than anything we would expect from one particle alone. Physics is filled with examples where a collection behaves in a way that no individual component can manage on its own. One water molecule is not wet. wetness becomes meaningful when many molecules interact. One atom does not have a temperature in the everyday sense, yet a large collection of atoms can be hot or cold. A single molecule does not freeze into ice, but many water molecules can organize themselves into a solid crystal. A magnet also depends on collective behavior. The material acts as a whole because enormous numbers of microscopic components become organized. Time crystals belong to this larger family of collective phenomena. Their repeating behavior is not the personal achievement of one particularly enthusiastic particle. It is something that emerges from the system. This collective aspect also explains why stability matters so much. Suppose you push a playground swing at slightly different intervals and it wobbles around in a complicated way. You might find moments when it accidentally returns to a similar position after every second push. That does not make it a time crystal. Accidental repetition is easy. Stable, collective repetition is the important part. In a genuine time crystal, the repeated response can remain locked to its characteristic rhythm even when the driving is not absolutely perfect. Small disturbances do not immediately destroy the pattern. The system is, in a sense, stubborn. It prefers to keep the repeating structure created by the interactions among its parts. This stubbornness is what makes the phenomenon look less like a carefully tuned toy and more like a genuine phase of matter. We usually learn about phases of matter through solid, liquid, and gas. Ice melts into water, water boils into vapour, and school science textbooks are reasonably satisfied with that for a while. Modern physics uses the word phase more broadly. A phase can describe a particular kind of collective organisation. Magnetism can define a phase. Superconductivity can define a phase. There are quantum phases whose behaviour cannot be understood merely by asking whether a material is solid or liquid. Time crystals fit into this broader way of thinking because the important feature is a pattern of order appearing in time. That does not mean the material itself becomes a crystal in the familiar mineral sense. A time crystal does not need to look like quartz. It does not have to be transparent. It does not sit on a shelf gently flashing at midnight. The systems used in experiments can involve carefully controlled quantum particles, trapped ions, spins in solid materials, or other arrangements designed so that the components can interact and be driven in the required way. What matters is not the shape of the object. What matters is what a measurable property of the system does as time passes. One common example involves quantum spin. Spin is a property of quantum particles, although the name can be misleading because the particle is not simply a tiny ball rotating like a planet. Quantum spin is an intrinsic property with its own unusual rules. For an intuitive picture, we can imagine many small quantum elements that can be found in different states. Researchers can manipulate those states with repeated pulses. If each pulse simply flips the state, and every component behaves independently, there's nothing especially remarkable. But when the particles interact strongly enough and the system is arranged correctly, the collective response can settle into a stable rhythm that takes more than one drive cycle to repeat. Consider again a repeated sequence of pulses. The first pulse arrives, then the second, then the third, each separated by the same amount of time. If the system exactly followed the drive, its measurable state would repeat after each pulse. In a discrete time crystal, it might require 2 pulses before the same state returns. One cycle produces one condition, the next produces another, and only after the following cycle does the original condition return. This pattern can continue in a remarkably regular way. The system is not ignoring the drive. The drive is essential. But the response has a structure that is not simply an obedient copy of the external timing. This point is worth holding on to because it prevents one of the most common misunderstandings. A time crystal is not a machine that starts moving and then somehow creates unlimited energy forever. The name naturally tempts people toward perpetual motion, especially because some descriptions say that a time crystal keeps oscillating. Physicists have spent centuries explaining why perpetual motion machines do not work, so the arrival of something called a time crystal understandably caused raised eyebrows. However, repeating behavior does not automatically mean useful energy is being produced. A system can display a persistent pattern without providing free power that can be extracted forever. The earliest ideas about time crystals did create a more serious difficulty. The original proposal imagined something even more extraordinary, a system in its lowest possible energy state that would still display continuous repeating motion. That would be an equilibrium time crystal, something that repeated in time without needing a periodic external drive. The idea was bold, and for a while it produced exactly the sort of excitement that bold ideas usually produce, followed almost immediately by physicists attempting to prove that it could not work. Eventually, theoretical results showed that the simplest version of this equilibrium idea could not exist under the proposed conditions. That might have ended the subject, but science rarely develops in such a tidy way. Instead of abandoning the entire idea, researchers changed the question. If a time crystal could not exist as a simple equilibrium system in the original sense, perhaps a related form of temporal order could appear in a system that was repeatedly driven and kept away from ordinary equilibrium. This turned out to be the more productive direction. The modern discrete time crystal emerged from that shift. It did not preserve every feature of the earliest proposal, but it kept the central insight that a physical system might spontaneously develop, repeating order in time. That word spontaneously also deserves care. It does not mean the system begins doing something for no reason. The system still obeys physical laws, and the drive still matters. Spontaneous symmetry breaking means that the governing setup allows several equivalent possibilities, but the system settles into a particular organized pattern. The choice is not explicitly written into the driving rhythm itself. The collective state creates the larger temporal pattern. A simple analogy can help. Imagine a dance instructor clapping at a steady pace. Everyone in the room hears the same clap. The instructor does not tell the dancers to divide themselves into alternating groups, but through interaction they begin following a pattern where one group moves on one clap and the other moves on the next. The full arrangement repeats only after 2 claps. The instructor supplies the timing, but the dancers create the larger pattern. If the group is strongly coordinated, a slightly mistimed clap does not immediately ruin the dance. The pattern survives. A time crystal involves something far more precise and quantum mechanical, but the key idea is similar. The system uses the repeated drive as a framework and creates a more elaborate repeating structure of its own. The reason quantum mechanics becomes so important is that many of the systems capable of showing time crystal behavior depend on delicate relationships among quantum states. Those relationships can be destroyed if energy spreads through the system in an ordinary thermal way. This creates another challenge. A repeatedly driven system normally absorbs energy. Keep pushing energy into a collection of particles and you might expect the system eventually to heat up until any special order is lost. If that happened quickly, the time crystal pattern would disappear. Researchers therefore need ways to prevent ordinary heating from wiping out the repeating behavior. Different approaches do this in different ways. Some use disorder and interactions to restrict how energy spreads through the system. Others use forms of controlled driving that allow long-lived ordered behavior. The technical details vary, but the underlying challenge is simple. The repeated pattern has to survive. It cannot merely appear for a moment and vanish as the system heats into a featureless state. This is one reason time crystals have become interesting beyond the novelty of their name. They offer physicists a way to study matter that is far from ordinary equilibrium. Most familiar thermodynamics describe systems moving toward equilibrium, where energy spreads out and large-scale properties become stable. Time crystals live in a less familiar territory. They are driven, they are dynamic. Their interesting order appears because they do not simply settle into the kind of quiet thermal balance we might expect. That makes them useful for asking a broader question about physics. What kinds of organized behavior can matter display when it is constantly being pushed, and yet somehow avoids losing all structure? For a very long time, phases of matter were mainly discussed in equilibrium. Heat something, cool it, apply pressure, change a magnetic field, and see what stable phase appears. Time crystals help strengthen a newer way of thinking, in which driven quantum systems can have their own distinctive phases and patterns. The subject also forces us to be careful about what we mean by repetition. When you watch a pendulum swing, you can point to the bob moving from left to right and back again. In a quantum time crystal, the repeating quantity may not be a visible object moving through space at all. It could be the orientation of spins, a pattern in measured correlations, or some other property that requires sensitive equipment to observe. Nothing has to glow. Nothing has to physically travel around a circle. The time crystal is defined by the behavior of the system, not by a particular visual appearance. That can make the idea feel less dramatic at first, but it is actually much more interesting. Physics often becomes stranger when we stop insisting that everything must look like a familiar machine. A time crystal is not a microscopic clock with gears. It is a form of organized quantum behavior. The clock comparison is useful only in the broadest sense that something repeats. Beyond that, the analogy begins to break. The name also encourages another mistaken picture, as though the crystal exists inside time rather than space. In reality, the physical system still sits in ordinary space like any other experiment. The temporal part refers to the repeating order in its behavior. An ordinary crystal has a repeating pattern when you move through position. A time crystal has a repeating pattern when you look at the system at different moments. The analogy lies in the structure of the repetition. This distinction becomes especially clear when we ask what would destroy a time crystal. If it were merely a clock, turning off the mechanism would stop it. In a time crystal, the relevant issue is whether the collective temporal order remains stable under disturbances, and whether the interactions that support it continue to operate. The system is not just counting time, it is organizing itself through time. That idea may sound small compared with black holes, warped space, or time travel, but it reaches surprisingly deep. It asks us to reconsider something very basic about order. We are used to patterns being arranged across space. Tiles on a floor repeat from one position to another. Atoms in a crystal repeat in a lattice. Waves create regular patterns. Time crystals show that under the right conditions, the language of order and symmetry can also be applied to repeated behavior through time. And once we begin thinking that way, the strange name becomes less mysterious. A time crystal is not time made solid. It is matter displaying a crystalline kind of order in its temporal response. It is a system that does not merely experience time while something happens within it. The timing of its behavior becomes part of the ordered state. There is still a great deal hidden inside that sentence. We have mentioned crystals, symmetry, quantum spin, collective behavior, driven systems, and phases of matter, all of which deserve more room than we have given them so far. The easiest place to continue is with the most familiar word in the name. Before we can really understand why physicists dared to call these systems crystals, we need to look much more carefully at what makes an ordinary crystal a crystal in the first place, because the answer is not its hardness, its shape, or its sparkle. The important clue has been sitting quietly inside salt, quartz, and countless other materials all along, in the repeating order of their microscopic structure. When we hear the word crystal, most of us picture something beautiful. Perhaps a piece of quartz catching sunlight on a windowsill, a diamond sparkling under a bright lamp, or a snowflake resting perfectly on a cold surface before it disappears. Crystals have always carried a certain sense of mystery. They look almost too organized to be natural, as though someone carefully designed their shapes and patterns before placing them into the world. For centuries, people have admired crystals for their beauty, their symmetry, and their unusual forms. But physics is interested in something much deeper than appearance. A crystal is not a crystal because it is shiny. It is not a crystal because it has sharp edges. It is not even a crystal because it looks perfectly ordered from the outside. The true secret of a crystal is hidden far beneath the surface, in the microscopic arrangement of its atoms. And this is where our journey toward understanding time crystals takes an important step. Before we can understand a crystal that creates a pattern through time, we first need to understand the kind of pattern that ordinary crystals create through space. The story begins not with something rare and exotic, but with something sitting quietly all around us. The minerals in rocks, the grains of salt in a kitchen cupboard, the ice forming in a freezer, and even the materials inside many modern technologies all reveal the same fascinating idea. Nature has a remarkable ability to take simple building blocks and arrange them into repeating structures. Imagine shrinking down until the world around you becomes completely unfamiliar. The table in front of you is no longer a smooth surface. The glass of water beside you is no longer a clear liquid. Everything becomes a landscape of atoms and molecules, far too small for our eyes to see. At this scale, matter does not appear solid in the way we experience it. Instead, it is a collection of tiny particles interacting through invisible forces. These particles are not arranged randomly. Under certain conditions, they settle into patterns. A crystal forms when atoms or molecules arrange themselves into a highly organized repeating structure. The same basic arrangement appears again and again across the material. If you could travel through the microscopic world inside a crystal, you would notice a kind of regularity. Move a certain distance in one direction, and you encounter the same arrangement. Move further and the pattern continues. The crystal is built from repetition. This idea is surprisingly powerful because repetition is one of the simplest forms of order. A completely random arrangement has no predictable structure. One atom might be close to another, or it might not. There is no clear pattern to follow. A crystal is different because the atoms have settled into a stable relationship with one another. They have found a structure that allows the entire material to exist in an organized state. But why do atoms organize themselves at all? After all, individual atoms are not tiny architects carrying blueprints and measuring tapes. They do not decide that a certain arrangement would look more elegant. They simply follow the laws of physics. Forces between atoms determine how they interact. Under the right conditions, those interactions lead naturally to order. A useful comparison is a group of people sitting in a theatre. If everyone enters randomly and chooses a seat without caring about anyone else, the arrangement might look chaotic. But imagine that everyone follows a simple rule. Perhaps each person wants to sit a certain distance from their neighbours, or perhaps everyone chooses the seat that gives them the most comfortable space. Without anyone designing the final arrangement, a pattern can appear. The organisation emerges from many small decisions following the same basic rules. Atoms behave in a similar way, although their world is governed by quantum physics rather than human preferences. They interact through forces, and the most stable arrangement is often the one that minimizes the energy of the system. The atoms settle into a pattern where the overall structure is comfortable, in a sense. Not comfortable like a warm chair or a soft blanket, but stable according to the rules of physics. This idea of stability is central to understanding crystals. The atoms in a crystal are not frozen because they have stopped moving completely. Even in a solid crystal, atoms continue to vibrate. They are constantly moving slightly because of thermal energy. The colder the crystal becomes, the smaller these vibrations tend to be, but the atoms are not perfectly still. A crystal is not a motionless collection of particles. It is an organized collection of particles that maintain a repeating structure, while still experiencing constant microscopic activity. This is already a useful reminder because our everyday language can sometimes mislead us. When we say something is solid, we often imagine it as completely fixed and unmoving. But at the microscopic level, even the hardest diamond contains atoms that are vibrating. The difference between a solid and a liquid is not that one has movement and the other does not. The difference is how the particles are organized and how freely they can move relative to one another. In a crystal, the atoms are arranged in a repeating pattern, because that arrangement is energetically favorable. In a liquid, the particles have more freedom to move around. They're still interacting, but they do not maintain the same long-range repeating structure. A gas is even less organized, with particles spreading out and moving more independently. The transition between these states reveals another fascinating idea. Crystals are not simply objects that happen to exist. They are the result of a process. When matter changes from one state to another, the particles can reorganize. Cooling water into ice is a perfect example. Liquid water molecules move freely, constantly rearranging themselves. As the temperature drops, the molecules lose energy and begin settling into a more ordered structure. The familiar shape of ice comes from this microscopic organization. Snowflakes provide one of nature's most beautiful examples of crystal formation. Each snowflake begins with water molecules arranging themselves into a structure influenced by temperature and humidity. The famous six-sided shapes appear because of the way water molecules bond together. Every snowflake is different, because the exact conditions during formation vary, but the underlying principles remain the same. A repeating molecular arrangement creates a recognizable form. This relationship between simple rules and complex patterns appears throughout physics. A snowflake does not need someone to draw its design. A crystal does not need a builder. The pattern emerges because the components interact according to consistent laws. The same idea helps explain why crystals are so closely connected to symmetry. Symmetry is a concept we encounter everywhere. A butterfly has symmetry between its wings. A circle looks the same when rotated. A perfectly balanced object appears unchanged when viewed in certain ways. In physics, symmetry is even more fundamental. It describes situations where something remains unchanged after a transformation. A crystal is interesting because it has a special relationship with symmetry. The laws of physics themselves often allow many possible arrangements, but the crystal chooses one particular repeating structure. This choice creates a form of order that did not exist before. Imagine a perfectly smooth field covered in snow. Every direction across the field is equivalent. There is no obvious feature telling you where one location is more important than another. Now imagine someone places a series of identical flags in evenly spaced rows across the field. The field itself has not changed. The underlying space is still uniform. But the arrangement of flags creates a pattern. Certain locations now matter more than others because the structure has selected them. Atoms in a crystal do something similar. The laws governing their interactions do not say that one particular position in space is special. Yet when the crystal forms, the atoms settle into a repeating arrangement that creates special positions. This is known as spontaneous symmetry breaking. It sounds complicated, but it appears in many places. A simple example is a pencil balanced on its tip. While the pencil is perfectly upright, every direction around it is equally possible. The system is symmetrical, but the moment the pencil falls, it chooses one direction. It could have fallen any way, but it ends up choosing one specific outcome. The laws of physics did not prefer that direction. The final state simply selected one possibility. Crystals work in a more complex way. The atoms could potentially arrange themselves in many equivalent ways, but when the crystal forms, one particular pattern emerges. The symmetry of the original situation is reduced because the organized structure has appeared. This idea becomes extremely important when we return to time crystals because the same language of symmetry breaking applies, but instead of positions in space, the pattern involves moments in time. Before making that connection, however, it is worth appreciating just how much ordinary crystals have taught physicists. Crystals are not only beautiful objects, they have been some of the most important materials in science and technology. The predictable arrangement of atoms gives crystals useful properties. Quartz crystals, for example, can vibrate at extremely regular frequencies when electricity is applied. This makes them valuable in clocks, watches, and electronic devices. Semiconductor crystals form the foundation of modern computers and smartphones. The organized structures inside materials allow scientists and engineers to control how electrons behave. In a sense, crystals are nature's demonstration that order can emerge from simple ingredients. A crystal does not contain different atoms arranged randomly like a collection of unrelated objects. Instead, the atoms cooperate through their interactions. The whole structure becomes something greater than the individual pieces. This is a recurring theme throughout physics. Many of the most interesting properties of matter appear only when large numbers of particles work together. A single atom cannot form a crystal. A single molecule cannot create a snowflake. A single particle cannot create the complex behavior of a magnet or a superconductor. The interesting physics often appears when enormous numbers of components interact. This is why time crystals are such a natural extension of the crystal idea. Ordinary crystals show us that matter can develop repeating order in space. They teach us that symmetry can be broken, and that collective behavior can create something new. Once physicists understood this, the question almost became unavoidable. If nature can create repeating patterns across space, could it also create repeating patterns across time? The question sounds simple, but it challenges our usual understanding of what a crystal is. Space is where we normally expect structure to exist. We imagine atoms arranged in rows, molecules forming shapes, and materials having physical patterns that we can observe. Time feels different. Time is something we experience passing. It is the background against which events happen. We do not usually think of time itself as something that can contain structure. Yet physics has a long history of discovering that our everyday intuition is incomplete. The universe is full of things that seem impossible until we learn the deeper rules. Space can bend. Time can pass at different rates. Particles can behave like waves. Empty space can have physical properties. The more carefully we examine reality, the more we discover that nature does not always follow the expectations created by ordinary experience. Time crystals belong to this tradition of surprising discoveries. They begin with the lessons ordinary crystals provide. A crystal is not defined by its appearance, it is defined by organized repetition. It is a system where many tiny components create a stable pattern through their collective behavior. The question is not whether time crystals look like crystals. The question is whether the idea of crystal order can be extended into a new direction. To answer that, physicists had to think carefully about what kind of repetition was possible. They had to separate ordinary motion from genuine order. They had to understand the difference between something simply changing and something developing a protected, repeating pattern. They had to explore what happens when quantum systems are pushed away from their usual behavior. And this is where the story becomes much stranger, because the next step was not simply discovering a new material. It was questioning one of the most familiar assumptions in physics itself, that time moves forward in a smooth and predictable way, without the possibility of forming its own kind of structure. The idea of a crystal that exists in time begins with a humble crystal sitting in space. But once we ask whether time can have its own patterns, we move into a part of physics where intuition starts to become less reliable, and where the smallest particles in nature begin revealing some very unexpected behavior. The repeating order inside an ordinary crystal gives us a useful way to approach the stranger kind of order that appears in a time crystal, but there is one idea sitting between the two that we need to understand properly before anything else makes sense. That idea is symmetry. In everyday conversation, symmetry usually means that two sides of something match. A face can be roughly symmetrical, a butterfly has wings arranged in a balanced way, and a snowflake can be rotated and still look surprisingly similar. Physics uses the word in a broader sense. A symmetry exists whenever we can make a particular change to a system without changing the physical rules that describe it. Sometimes that change involves turning something around. Sometimes it involves reflecting it. Sometimes it means moving the entire experiment from one place to another. And sometimes, more strangely, it means moving the experiment from one moment to another. This last possibility is where time crystals begin to become understandable, because the important symmetry involved is not the symmetry of a shape at all. It is the symmetry of time itself, or more precisely, the fact that the fundamental rules governing a system can remain the same when we shift when we look at it. Imagine performing a simple experiment in a quiet laboratory. You place a ball on a table, give it a push, and observe what happens. Suppose you perform the same experiment again an hour later, under exactly the same conditions. Physics does not normally contain a rule saying that the ball must behave differently, simply because it is now an hour later. If the table, the ball, the temperature, and everything relevant to the experiment are the same, then the laws governing the motion are also the same. You could repeat the experiment tomorrow or next Tuesday and expect the same physical principles to apply. The universe does not appear to reserve a different version of mechanics for Tuesday afternoons. This independence from the absolute time at which an experiment is performed is an example of time translation symmetry. The phrase translation sounds as though something is being converted from one language to another, but in physics it simply means shifting. A spatial translation means moving something from one position to another. A time translation means shifting from one moment to another. If the physical description remains unchanged after that shift, the system has that symmetry. Ordinary crystals already teach us how asymmetry can be present in the underlying rules, and yet not be fully respected by the state that matter chooses. Consider empty, uniform space before a crystal forms. There is nothing in the basic laws that marks one microscopic location and announces that an atom must sit exactly there. Shift the entire arrangement a little to the left before the crystal forms, and the laws remain the same. Yet once the atoms settle into a crystal lattice, the situation changes. The atoms occupy a repeating set of preferred positions. Move by a very small arbitrary distance, and the structure no longer lines up with itself. Move by exactly the spacing between repeating parts of the lattice, however, and the structure matches again. The continuous freedom to shift by any distance has been reduced to a smaller set of special shifts. The underlying physical laws allowed all positions to be treated equally, but the crystal selected a particular repeating arrangement. That is the essential meaning of spontaneous symmetry breaking in an ordinary crystal. The word spontaneous can be misleading because it sounds as though something happened without a cause. That is not what physicists mean. The atoms still obey physical laws, forces still act, and energy still matters. Spontaneous means that the laws themselves do not uniquely choose the particular version of the ordered state that appears. Imagine balancing a pencil perfectly upright on its tip. While it is balanced, every direction around it is equivalent. Nothing about the table says the pencil must fall north rather than south, east rather than west. Eventually it falls, and once it does, one direction has been selected. The symmetry of the original situation is no longer present in the final state, even though the underlying laws never preferred that particular direction. A crystal does something conceptually similar, on an enormously more complicated scale. Its microscopic components collectively choose an ordered arrangement from many equivalent possibilities. The state becomes less symmetrical than the laws that allowed it to form. The remarkable step behind a time crystal is to ask whether something similar can happen with time rather than position. Instead of matter selecting a repeating arrangement of locations, could a physical system select a repeating arrangement of moments? That question sounds peculiar, because we are not accustomed to thinking about moments as places where a pattern can live. A chair can occupy one location rather than another. An atom can sit at one point in a crystal lattice. But a moment seems to disappear as soon as it arrives. We experience time as a sequence, so the idea of constructing order across that sequence does not immediately feel as natural as constructing order across space. Physics, however, does not require our intuition to feel comfortable before it begins asking questions. To see what temporal symmetry breaking means, it helps to start with a system that is deliberately driven at a regular rhythm. Imagine a laboratory apparatus that sends an identical pulse into a collection of quantum particles once every fixed interval. The entire driving procedure repeats again and again. From the perspective of the external controls, each cycle is equivalent. One pulse is followed by the same arrangement of controls as the next pulse, and then the same thing happens again. The system therefore has a discrete time translation symmetry imposed by the drive. Continuous time translation symmetry is already absent, because the apparatus is doing something specific at particular stages of every cycle. A moment halfway between two pulses is not equivalent to the moment when the pulse arrives, but shifting forward by one complete driving cycle does bring the external setup back to the same point in its pattern. This distinction between continuous and discrete symmetry is much easier than the terminology makes it sound. A system with continuous time translation symmetry does not care how far you shift the clock. Shift by a second, a fraction of a second, or an hour, and the underlying rules remain the same. A periodically driven system has a more limited symmetry. It repeats only after certain intervals, rather like an ordinary crystal, repeating only after certain distances. That is why physicists call the symmetry discrete. Only particular shifts return the system to the same driving conditions. Once we have that repeating external rhythm, a new possibility appears. The particles might respond by repeating with exactly the same rhythm as the drive, which would be the unsurprising outcome. But under the right conditions, they can instead organize themselves into a stable response that takes several driving cycles before it repeats. Suppose the external pulse comes once during every cycle, and the system is arranged so that its observable state alternates between two conditions. After the first pulse, it appears one way. After the second pulse, it appears another way. After the third pulse, it returns to the first condition, and after the fourth, it returns to the second. The external drive repeats after every cycle, but the full behavior of the system repeats only after two cycles. The drive says that each cycle should be equivalent. The state of the system says otherwise. It distinguishes alternating cycles from one another. In that sense, the state has less time translation symmetry than the driving rules. The original discrete time translation symmetry has been spontaneously broken into a larger repeating pattern. This is one of the most important points in understanding a discrete time crystal, because simply oscillating is not enough. Nature contains countless oscillators. A pendulum oscillates, a guitar string vibrates, an alternating electrical signal repeats. A planet moves periodically around a star. None of these things automatically qualifies as a time crystal. Even a system responding at a slower rhythm than an external drive is not necessarily enough on its own, because ordinary nonlinear systems can produce complicated responses, including rhythms that repeat after several driving cycles. The defining behavior of a time crystal has to be collective and robust. The particles must interact in such a way that the new temporal order belongs to the phase of the system, rather than appearing only because someone tuned the apparatus to one delicate setting. That robustness is easier to appreciate with a slightly imperfect example. Imagine a large room filled with people who are supposed to turn around whenever a light flashes. If every person simply watches the light independently, small errors in the flashes will quickly create a mess. Some people will turn early, others late, and before long the group will lose any clear pattern. Now imagine that everyone is also paying attention to their neighbours. If one person becomes slightly mistimed, the surrounding people influence them back toward the shared rhythm. The group develops a collective pattern that can survive small mistakes in the external signal. A time crystal has a related kind of rigidity, although the actual mechanism is quantum mechanical and depends on interactions within the system. The response does not immediately drift just because the driving pulse is slightly imperfect. The many-body system helps lock the behavior into its characteristic temporal pattern. This is one reason physicists speak of time crystalline order rather than merely repeated motion. Order implies that the behavior is coordinated across the system. Many components participate in a shared pattern. In a spatial crystal, one atom does not create the lattice by itself. The crystal exists because a huge collection of atoms maintains a related arrangement over long distances. In a time crystal, The corresponding idea is that the temporal response is not simply the private oscillation of one isolated particle. The order is supported by correlations and interactions among many parts of the system. Observing one component can tell us something about the collective temporal pattern because the components are not behaving independently. The comparison with ordinary crystals becomes even clearer if we imagine walking through a crystal lattice. At an arbitrary distance, the microscopic arrangement looks different. Move by the correct lattice spacing and the pattern lines up again. A discrete time crystal asks us to perform a similar mental journey, except instead of moving a microscope through space, we move our observation forward through the driving cycles. Looking after one cycle may show a different state. Looking after another may still show something different. After the correct number of cycles, the temporal pattern lines up with itself again. The repetition is not a row of atoms occupying positions. It is a sequence of states occupying moments in the evolution of the system. There is another subtle part of spontaneous symmetry breaking that becomes particularly interesting in time. If a system develops a pattern that repeats after 2 driving cycles, there can be more than one equivalent way for that pattern to align with the external drive. The system might begin in one condition on the first cycle and the other condition on the second, or it might begin the other way around. The external driving protocol itself does not have to choose between these alternatives. The system settles into one of them. This is closely related to the freedom an ordinary crystal has to place its lattice in one of many equivalent positions. The laws do not mark one location as the required starting point for the crystal pattern. In temporal symmetry breaking, the rules similarly need not specify which part of the emergent pattern must coincide with a particular driving cycle. At first, this can seem like a technical detail, but it goes to the heart of the word spontaneous. If the external machine explicitly ordered the system to behave differently on alternating cycles, then the symmetry would not be spontaneously broken by the system. The difference would already be written into the drive. Imagine a lamp controlled by a programmer who deliberately makes it bright on one pulse and dim on the next. The lamp repeating every 2 cycles tells us nothing surprising, because the 2-cycle pattern was programmed from the start. A time crystal is different because the external driving remains symmetric from one cycle to the next, while the system develops a response with a larger period. The extra structure appears in the state rather than being directly written into the instructions. This also explains why physicists became interested in whether the response could survive disturbances. A pattern that appears only at one perfectly tuned value might simply be an ordinary resonance or a fragile dynamical coincidence. A phase of matter should occupy a region of possible conditions. Small changes should not immediately erase the defining behavior. In a discrete time crystal, interactions between the components can produce this rigidity. Change the driving slightly, and the system may continue responding at the same locked temporal rhythm, instead of smoothly changing its period to follow the imperfection. That resistance is evidence that we are looking at collective order. The importance of interaction is worth emphasizing because without it, we could create many individual objects that happen to perform similar oscillations and mistakenly call the result a crystal. Imagine placing hundreds of identical metronomes on separate tables and starting them at roughly the same moment. They may tick together for a while, but tiny differences eventually pull them apart. Each metronome keeps its own time. There is no shared phase of matter connecting them. If instead the oscillators can influence one another, collective synchronization becomes possible. Time crystals are not merely synchronized metronomes, but this contrast helps show why many body interactions matter. The temporal order must belong to the interacting system, rather than being a coincidence produced by many independent components. Quantum systems make this story more complicated because repeatedly driving them usually creates a problem. Each pulse can transfer energy. Continue driving and energy can spread among the particles. In many systems, this eventually produces heating and destroys whatever delicate order existed. The particles forget the organized state they started in and move toward behavior that looks increasingly thermal and featureless. A long-lived discrete time crystal therefore needs some mechanism that protects the temporal order from being rapidly washed away. Early theoretical models often relied on many-body localization, where disorder and interactions can prevent energy from spreading through the system in the usual way. Other approaches developed later can stabilize time crystalline behavior through different mechanisms. The details vary, but the general requirement remains the same. The system must avoid quickly absorbing the drive in a way that destroys the repeating pattern. This is where the idea begins to separate sharply from the popular image of a mysterious object ticking forever. A time crystal is not remarkable because it possesses some magical source of endless motion. Its unusual property is the organization of its response. It is a question of symmetry and phase structure, not free energy. The system can repeat without becoming a perpetual motion machine, because periodic behavior does not automatically mean that useful work can be extracted forever. A planet can orbit for an extremely long time without functioning as a limitless energy generator. A quantum state can show persistent oscillatory structure without secretly violating thermodynamics. The difficult scientific question is not how the time crystal creates energy from nothing. It does not. The question is how its temporal order can remain stable under the conditions that normally cause driven systems to lose order. There is also a useful distinction between the discrete time crystals most commonly discussed and the older dream of a continuous time crystal. In the discrete case, an external periodic drive has already selected a basic rhythm. The system then breaks that remaining discrete symmetry by responding with a larger period. A continuous time crystal would be more radical. There, the underlying setup would not contain a periodic external clock telling the system when each cycle begins. The system would somehow develop persistent periodic behavior, while the underlying description remained continuously symmetric in time. This was closely related to the earliest proposals, and it immediately raised difficult questions about equilibrium, lowest energy states, and whether a system could genuinely oscillate forever without an external periodic drive. Those questions turned out to be much harder than the name time crystal initially suggested. Symmetry breaking in space was well understood. Physicists knew how crystals selected positions, how magnets selected orientations, and how different faces of matter could emerge when an underlying symmetry was lost. Extending the same reasoning to time seemed natural, but time does not behave exactly like another ordinary spatial direction in quantum mechanics. A ground state is supposed to be a stationary state. Asking that same state to display observable periodic motion creates tension with the mathematical structure of equilibrium quantum theory. That tension would eventually become one of the decisive issues in the early history of the subject. Even before reaching that historical argument, we can see why the proposal attracted attention. The idea took something familiar and shifted it in a direction that had rarely been considered. Physicists had spent generations classifying matter according to how it organized itself in space. They understood lattices, magnetic domains, superconducting phases, and many other forms of collective order. Time crystals suggested that the catalogue might be incomplete. Perhaps matter could organize itself not only according to where its components are, but according to when particular states recur. This does not mean that time itself is being broken. Nothing cracks in the flow of seconds. The phrase broken time translation symmetry refers to the relationship between the symmetry of the governing conditions and the symmetry of the state that appears. The laws can treat repeated cycles as equivalent while the system does not. That is a much more precise statement than saying a time crystal somehow damages time, although admittedly the less precise version would probably sell more cinema tickets. It also helps to separate time translation symmetry from the arrow of time. The arrow of time concerns the familiar distinction between past and future, including the tendency for entropy to increase. Time translation symmetry asks a different question. It asks whether the rules change when we shift the experiment along the time axis. A system can have time translation symmetry while still possessing a clear distinction between earlier and later events. Breaking time translation symmetry does not make the future become the past, and a time crystal does not reverse time. The subject sounds as though it should involve time travel, but the actual physics is about periodic order. Once that is understood, the phrase time crystal becomes almost surprisingly literal. An ordinary crystal takes a continuous spatial symmetry and replaces it with a repeating spatial pattern. A discrete time crystal begins with a system whose drive repeats after a fixed interval, and develops a state that repeats only after a larger interval. In both cases, the ordered state respects less symmetry than the rules that support it. In both cases, many components participate in the order. In both cases, the pattern has to be stable enough to deserve being called a phase rather than an accident. The difference is that ordinary crystals have been sitting in rocks for billions of years, while time crystals had to be imagined before anyone knew whether the idea could survive the rules of quantum mechanics. Once physicists began asking seriously whether time translation symmetry could break, the discussion moved very quickly from an elegant analogy to a difficult argument about what nature actually permits. The first proposal was bold enough to suggest a system that could display temporal order in its lowest energy state. Then came objections showing why the simplest version could not work. Instead of killing the idea, those objections forced researchers to reshape it, moving away from the original equilibrium picture and toward driven quantum systems where discrete time symmetry could genuinely break. That unexpected path from a speculative proposal to something laboratories could test is where the story of the time crystal really begins. Once physicists had learned to describe an ordinary crystal as a system that breaks a symmetry of space, the next question was almost inevitable. If matter can organize itself so that a repeating pattern appears from place to place, could it organize itself so that a repeating pattern appears from moment to moment? For a long time, that question remained more like an intellectual curiosity than a serious research program. Oscillating systems were already everywhere in physics. Pendulums swung, atoms vibrated, electromagnetic waves repeated, planets returned to familiar positions, and clocks had been keeping regular rhythms for centuries. None of that required a new phase of matter. The challenge was much more specific. Physicists wanted to know whether a system could spontaneously break time translation symmetry in the same meaningful sense that a crystal breaks spatial translation symmetry. In other words, could matter settle into a state whose temporal pattern was more structured than the laws governing it required? The question sounded simple enough to ask over a cup of tea. Answering it took several years of arguments, failed ideas, revised definitions, and experiments involving some of the most carefully controlled quantum systems ever built. The modern story began in 2012 with physicist Frank Wilczek. He asked whether the familiar concept of spontaneous symmetry breaking could be extended into time. The comparison with an ordinary crystal was direct. In empty space, no particular position is fundamentally preferred. But when a crystal forms, atoms occupy a repeating set of locations. The resulting state is less symmetric than the underlying laws. Wilczek wondered whether a similar thing could happen in time. Perhaps a quantum system in its lowest energy state could somehow develop persistent periodic behavior, repeatedly changing while remaining in the most stable state available to it. Such a system would not merely be a clock someone had wound up. Its repeated motion would be part of the state itself. If that were possible, it would represent a new type of spontaneous order, and the name time crystal seemed almost unavoidable. There was something immediately appealing about the proposal because it connected two familiar ideas in an unfamiliar way. Crystals were among the oldest known examples of ordered matter, while time was among the most fundamental ingredients in physics. Put them together, and the result seemed both elegant and slightly suspicious. The suspicious part came from the phrase lowest energy state. In quantum mechanics, the lowest energy state of a system is usually called its ground state, and a ground state is expected to be stationary in a very important sense. Its measurable properties are not normally supposed to perform a permanent repeating dance without some external influence. Asking for a ground state that continuously changes in an observable way therefore created tension almost immediately. This did not mean the proposal was foolish. Quite the opposite. Good theoretical questions often become valuable precisely because they expose a boundary between what our intuition suggests and what the mathematical structure of a theory permits. Wilczek was asking whether physicists had been too narrow in the way they thought about symmetry breaking. If spatial order could arise spontaneously, perhaps temporal order could as well. The analogy was strong enough to deserve investigation, and soon researchers began examining exactly what such a system would have to do. It also did not take long for problems to appear. One of the early responses came from physicist Patrick Bruno, who analysed proposed versions of spontaneously rotating time crystals and argued that the kind of permanent ground state motion being imagined could not occur for a broad class of systems. The details involved careful quantum reasoning, but the basic difficulty can be understood without mathematics. If the system is genuinely in its lowest possible energy state, there should be no lower energy arrangement available for it to fall into. That sounds promising if you want something stable, but a stable ground state is not the same thing as an object endlessly cycling through distinguishable configurations. In ordinary quantum mechanics, a true energy eigenstate evolves in a way that does not produce the sort of observable, periodic change required by the original time crystal picture. A simple comparison helps. Imagine a ball resting at the bottom of a bowl. The ball is in the lowest position available to it. If it were rolling endlessly around the bowl, then it would have kinetic energy and would no longer resemble the simple lowest energy configuration we started with. Quantum mechanics is not literally a ball in a bowl, of course, but the intuition captures part of the conflict. The original dream wanted the security of a ground state together with a permanent observable rhythm, and those two requirements did not fit together as easily as the crystal analogy first suggested. The criticism became more general over the next few years. Haruki Watanabe and Masaki Yoshikawa developed a careful definition of what time crystalline order should mean, and showed that the hoped-for continuous time crystal could not exist in ordinary equilibrium ground states or thermal equilibrium states under broad conditions. This result was important because it did more than reject one clever model. It showed that the problem was built into the structure of equilibrium quantum systems more generally. If you insisted that the system remain in equilibrium and asked it to spontaneously break continuous time translation symmetry in the original way, nature appeared to say no. At this point, the story could easily have ended. Physics is full of attractive proposals that disappear after a no-go theorem shows why they cannot work. Someone has an elegant idea, other researchers test it against deeper principles, and the idea becomes an interesting footnote. Time crystals might have joined that collection. Instead, something more productive happened. Researchers began changing the question. The important realization was that the no-go results applied to equilibrium systems of the original type. They did not necessarily forbid every possible form of time crystalline order. Equilibrium was the restriction. Remove that restriction, and a much larger landscape opened up. This is where periodically driven quantum systems entered the story. Instead of asking for a system that sits quietly in its lowest energy state and somehow begins oscillating on its own, physicists considered systems that are deliberately driven over and over. A repeated external pulse already creates a rhythm. The system is no longer in ordinary equilibrium because something is continuously being done to it. At first that might sound like cheating. If you repeatedly push a system and it repeatedly responds, surely you have simply built a clock. But that is not what researchers were looking for. The interesting possibility was that the system could respond with a stable rhythm, different from the rhythm of the drive. Suppose an experimental control acts once during every cycle. From the outside, each cycle is equivalent. The same procedure repeats. If the system simply returns to the same state after every cycle, It respects the timing of the drive. There is nothing time crystalline about that. But imagine that the system requires 2 driving cycles before it returns to the same state. The external conditions repeat after every cycle, while the physical response repeats only after every second cycle. The system has created additional temporal structure that was not explicitly programmed into the drive. That distinction rescued the central idea of symmetry breaking. The continuous time symmetry of the earliest proposal was gone because the external drive already picked out a repeating interval. But a discrete version of time translation symmetry remained. Every driving cycle was equivalent to every other one. If the system spontaneously settled into a response that required several cycles to repeat, then even that discrete symmetry would be broken. The resulting phase became known as a discrete time crystal. The idea began to take a precise modern form around 2016. Several groups studying driven many-body quantum systems realized that interactions and disorder could create phases with exactly this kind of robust temporal response. Work by Vedika Khemani and colleagues investigated the phase structure of periodically driven quantum systems, while Dominic Else, Bella Bauer, and Chetan Nayak developed a clear framework for what they called Floquet time crystals. Floquet is a term physicists use when dealing with systems governed by something that repeats periodically in time. The terminology may sound specialized, but the central picture is simple. The laboratory provides a repeating schedule, and the many-body system responds by developing a larger repeating schedule of its own. The word many-body is essential here. If one isolated particle happened to alternate between 2 states after repeated pulses, the behavior could easily depend on precise tuning. Change the pulse slightly and the pattern might drift away. A genuine phase of matter should be more resistant than that. Many particles interacting together can stabilize a collective response. Instead of each component trying to keep time independently, the components help enforce a common pattern. If the drive is slightly imperfect, the system can remain locked into the same larger period. This property became known as rigidity. It separated the proposed time crystal from an ordinary resonance. Resonances can also produce responses at frequencies related to an external drive, and classical systems can show all sorts of complicated periodic behavior. The time crystal claim required something stronger. The response had to be stable over a range of conditions and associated with collective many-body order. Small mistakes in the pulse could not simply move the system to a slightly different frequency. The temporal pattern had to behave like a phase rather than a coincidence. There was still another serious problem. Periodically driving a quantum system usually pumps energy into it. If you keep disturbing a collection of particles, they tend to absorb energy and eventually lose the special structure they started with. The system heats, in a generalized quantum sense, and the interesting order can disappear. A time crystal needs to maintain a clean temporal pattern, so ordinary heating is its enemy. One early solution involved many-body localization. Disorder can sometimes prevent interacting quantum particles from freely exchanging energy across a system. Instead of quickly forgetting their initial structure and reaching thermal equilibrium, the system can retain memory for a very long time. In the early theories of discrete time crystals, this offered a way to protect the repeating temporal order. The periodic drive could continue, but the many-body system would not simply absorb energy until every special feature vanished. Interactions helped establish the collective pattern, while localization helped keep the pattern from being washed away. This combination produced something that the original equilibrium proposal could not. The system was not claiming to move forever in its ground state. It was openly non-equilibrium. It was being driven. Yet its response still displayed spontaneous symmetry breaking because the system chose a temporal pattern, larger than the pattern imposed by the drive. The impossible version had been replaced by a physically allowed relative. That change is one of the most interesting parts of the time crystal story. Scientific ideas rarely move in a straight line from prediction to confirmation. Sometimes the first version is wrong in exactly the way needed to reveal the right question. The no-go theorems did not merely destroy the original proposal, they clarified what a time crystal could not be, which helped researchers identify what it could be. Instead of a perpetual ground state oscillator, the useful concept became a non-equilibrium phase with robust temporal order. Theory now had something laboratories could attempt to create. Creating it was not straightforward. Researchers needed quantum systems that could be controlled repeatedly, measured carefully, and kept sufficiently isolated from the outside environment. They needed many interacting components, because the collective nature of the response mattered. They needed a way to introduce a periodic drive. They needed imperfections, or at least the ability to test whether the behavior survived imperfections. And they needed the system to maintain coherence and order long enough for the characteristic pattern to become unmistakable. Two experimental approaches soon became especially important, and both reported observations in 2017. One experiment used a chain of trapped atomic ions. Ions are atoms that carry electrical charge, which allows researchers to hold them in place using electromagnetic fields. In a carefully controlled trap, a row of ions can behave like a highly adjustable quantum system. Their internal states can act as quantum spins, and laser pulses can manipulate them with impressive precision. Interactions among the ions allow information about one part of the chain to influence the others. The researchers applied a repeated sequence of operations to this chain. One part of the sequence manipulated the spins, while another allowed the spins to interact. If everything behaved as a simple collection of independent particles, slight imperfections in the manipulation would cause the response to drift. Instead, under the appropriate conditions, the interacting system produced a robust response whose period was longer than that of the driving sequence. The system returned to its original pattern after multiple drive cycles, rather than after every single one. This was the signature the theory had predicted. The detail that made the result convincing was not merely that an oscillation had been observed. Oscillations are cheap. Physics has never suffered from a shortage of things that wiggle. The important feature was that the response remained locked near the expected subharmonic rhythm, even as the experimental conditions were varied. That behavior suggested a collective phase rather than a carefully tuned accident. At roughly the same time, another group demonstrated time crystalline order using a very different physical platform involving spins associated with defects in diamond. A perfect diamond is built from carbon atoms arranged in a crystal lattice, but real and intentionally engineered diamonds can contain defects where the atomic structure differs from the perfect pattern. Certain defects can host quantum spin states that scientists can control with electromagnetic radiation and observe using light. The experiment involved a large collection of these spins interacting inside the diamond. Once again, researchers applied a repeated driving sequence, and once again, the system developed a response that repeated at a longer period than the drive itself. The fact that a similar kind of temporal order appeared in such a different system was encouraging. One experiment used trapped ions arranged with exquisite control. The other involved a disordered interacting spin system inside a solid material. The underlying details were different, but both pointed toward the same broader physical idea. This was the moment when time crystals changed status. A few years earlier, they had been a provocative theoretical suggestion whose simplest form appeared impossible. Now there were laboratory systems showing the kind of discrete time translation symmetry, breaking that the revised theory predicted. The phrase time crystal was no longer referring only to a speculative analogy. Even so, the experiments did not produce a magical object that could be removed from the apparatus, placed on a desk, and watched ticking indefinitely. The time crystal was a phase expressed through the dynamics of the controlled system. The driving protocol mattered. The interactions mattered. Isolation from the environment mattered. Measurement mattered. If the necessary conditions were removed, the temporal order would not simply continue as though someone had wound a supernatural watch. That distinction is especially important because public descriptions of time crystals often drift toward phrases such as matter, that moves forever. Such language sounds impressive, but it can create exactly the wrong mental picture. The scientific achievement was not the invention of endless motion. The achievement was the observation of spontaneous temporal order in a driven quantum many-body system. There was also no single moment when a lump of new matter suddenly appeared, and everyone agreed that the problem was finished. Theoretical definitions continued to develop. Researchers explored different mechanisms for stabilizing time crystalline behavior. Experiments moved beyond the earlier systems. New versions appeared that did not rely on exactly the same localization mechanism. Scientists investigated pre-thermal time crystals, open systems, dissipative settings, and other ways temporal order might survive. The name remained the same while the family of physical situations associated with it became broader. That is fairly normal in condensed matter physics. A phase of matter is not usually defined by one particular material or one experimental machine. Ferromagnetism is not tied to one piece of iron. Superconductivity is not a trick performed by one specific wire. The deeper goal is to identify the organizing principle that different systems can share. For time crystals, that principle is the stable breaking of time translation symmetry through collective dynamics. The historical path also explains why there is sometimes confusion when people read older descriptions of the subject. An early article may discuss a ground state time crystal and sound very different from a modern description involving periodically driven systems. Both belong to the same story, but they refer to different stages of the idea. The first proposal asked whether continuous time translation symmetry could break in equilibrium. The strongest results showed that the original version was not physically available under broad ordinary conditions. The later breakthrough involved discrete symmetry, breaking in non-equilibrium driven systems. Calling both ideas time crystals, without explaining that shift can make it seem as though physicists first proved time crystals impossible, and then somehow ignored their own proof. What actually happened is subtler. One definition was ruled out and a related but distinct form survived. There is something reassuring about that process because it shows how physics corrects itself, without necessarily throwing away every useful intuition. The analogy with ordinary crystals was not worthless simply because the first implementation failed. The deep connection between symmetry breaking and periodic order remained. Researchers only had to discover the conditions under which the analogy became physically meaningful. It is a little like trying to build a boat based on the observation that birds can cross the ocean. The first attempt might involve attaching wings to the boat, which turns out to be a terrible idea. That failure does not prove that crossing the ocean is impossible. It proves that wings were the wrong mechanism. The destination can remain while the route changes. Time crystals followed that sort of route. The first destination was temporal order. The original mechanism was an equilibrium ground state that oscillated spontaneously. That mechanism failed. The successful route passed through non-equilibrium physics, periodic driving, interacting quantum particles, and robust subharmonic response. And this route revealed something broader than the existence of one exotic phase. It showed that driven quantum systems could possess forms of organization that do not fit comfortably into the old picture of matter, simply settling toward equilibrium. For generations, much of statistical physics had focused on what systems do after they are left alone long enough. They exchange energy, approach thermal states, and lose detailed memory of how they began. Time crystals help to draw attention towards systems that are never allowed to settle down in the usual way, yet still develop stable and recognizable order. That is a peculiar combination. The system is continually being driven, so it is not at rest. Yet the repeated behavior can be stable enough to classify. It is dynamic without being arbitrary. It is out of equilibrium without being completely chaotic. And its order is visible not mainly by examining where its components sit, but by examining how their collective state returns through time. The first successful experiments therefore did more than confirm an unusual prediction. They gave physicists a new laboratory for studying how quantum matter behaves under repeated driving. They provided a place to test ideas about localization, thermalization, interactions, coherence, and the stability of non-equilibrium phases. The dramatic name attracted attention, but the deeper scientific value came from the questions hiding underneath it. That brings us naturally to the practical problem that confronted every experimental team interested in the subject. Once theory says that a time crystal can exist under the right conditions, what exactly do you put in the laboratory? You cannot order one from a catalogue. There is no jar labelled time crystal beside the magnets and cables. You have to create a quantum system with the correct ingredients, prepare its components, make them interact, apply a repeating drive, prevent ordinary heating from destroying the pattern, and then prove that what you are seeing is genuinely time crystalline, rather than an ordinary oscillation wearing a very impressive name. That is where the story moves from the strange birth of the idea to the even stranger business of actually building one. Once the idea of a discrete time crystal had survived the theoretical arguments, the next problem was wonderfully practical. How do you actually make one? It is one thing to say that an interacting quantum system can develop a stable repeating pattern in time. It is another thing entirely to walk into a laboratory and arrange for matter to do it. There is no raw material called time crystal that can be ordered by the kilogram. There is no furnace in which ordinary matter is melted and cooled until time begins repeating differently. Building a time crystal means creating a carefully controlled quantum system, preparing its microscopic components in a known state, making those components interact, disturbing them according to a repeating schedule, and then watching to see whether the entire system develops the distinctive rhythm predicted by theory. None of these steps is individually mysterious. The difficulty comes from making all of them work together while preventing the outside world from ruining the experiment before anything interesting has time to happen. The first ingredient is a collection of quantum objects that researchers can control. These might be trapped ions, quantum spins inside a solid, superconducting quantum devices, or other systems whose states can be prepared and measured with great precision. The exact material is less important than the abilities it gives the experimenter. Researchers need some property that can play the role of a microscopic two-state system, because the time crystal behavior is often observed by watching many such elements switch between different quantum states. Spin is frequently used for this purpose. As we have already seen, quantum spin should not be imagined too literally as a tiny ball physically rotating. It is an intrinsic quantum property, but for a simple mental picture we can treat each spin as something that can be prepared in one of two distinguishable orientations and manipulated with carefully timed pulses. Now imagine a row of these quantum spins. If they were completely independent, building a time crystal would be much harder. You could manipulate each one with a repeating pulse and make it change state, but small errors would accumulate. One spin might respond slightly faster than another. Another might experience a pulse that is a little too strong. After enough cycles, the neat collective pattern would drift apart. You would have a collection of microscopic oscillators, but not the rigid temporal order that makes a time crystal interesting. So the second ingredient is interaction. The components need to influence one another. Interaction allows the system to behave collectively. Instead of every spin trying to follow the external drive by itself, the spins become linked through the physics of the many-body system. Their behavior can become coordinated. This is rather like a group of people trying to clap together. If everyone is wearing headphones and listening to slightly different recordings, the clapping soon becomes untidy. But if everyone can hear everyone else, small mistakes can be corrected because the group provides a shared rhythm. Quantum interactions are obviously more complicated than people clapping in a room, but the comparison captures why isolated components are not enough. Time crystalline order is a property of the collective system. The third ingredient is the repeated drive. A discrete time crystal does not simply sit in the laboratory doing nothing while a hidden clock runs inside it. Researchers actively apply a sequence of controlled operations over and over. Depending on the experiment, These operations might be laser pulses, microwave pulses, magnetic manipulations, or carefully timed changes in the forces acting on the particles. The sequence repeats at a regular interval. That interval provides the basic temporal symmetry that the time crystal will later break. Suppose a pulse is designed to change the state of each spin. Ideally, one pulse might turn every spin from one orientation to the opposite orientation. Apply another identical pulse and the spins return. If everything were perfectly controlled, the system could alternate indefinitely, but that by itself would not prove very much. You have deliberately told the spins what to do. It would be like programming a lamp to turn on, then off, then on again, and announcing that the lamp had discovered temporal order. The more revealing experiment deliberately allows imperfection. The pulse can be made slightly too weak or slightly too strong. An ordinary collection of independent spins should gradually lose its clean rhythm because the error accumulates. After one pulse, each spin is a little away from where it should be. After another pulse, the error grows. Continue the process, and the original alternation becomes blurred. If the system contains the right interactions, however, something more interesting can happen. The collective behavior can remain locked into a stable pattern, even though the individual pulses are not perfect. This rigidity is one of the signatures researchers look for. The time crystal is not impressive because the laboratory can produce a repeating response when everything has been adjusted with impossible precision. The important result is that the response survives when the controls are changed slightly. The temporal pattern belongs to a region of physical behavior rather than a single magical setting on a machine. Think of pushing a child on a swing. If you alter the timing of your pushes, the swing responds differently. Its rhythm depends closely on the details of the driving. Now imagine a system that insists on returning to a particular larger rhythm despite small changes in when or how strongly you push it. That stubbornness would immediately tell you that something inside the system is helping organize the motion. In a time crystal, that something is the many-body interaction among quantum components. The laboratory therefore needs a balance between control and imperfection. Researchers need enough control to know exactly what they are doing, but they also need to demonstrate that the resulting pattern is not simply a consequence of perfect control. Science occasionally requires making an experiment slightly worse on purpose, which is one of those things that sounds irresponsible until someone explains the reason. Another major difficulty is heating. Repeatedly driving a physical system means repeatedly giving it opportunities to absorb energy. In an ordinary many-body system, that energy can spread among the particles. The system gradually loses memory of its carefully prepared state and moves towards something more thermal. Once that happens, the organized temporal pattern disappears. Instead of a clean repeated response, researchers are left with a complicated collection of particles that has effectively forgotten what it was supposed to be doing. A time crystal therefore needs some protection from ordinary thermalization. In some of the earliest theoretical models, this protection came from many-body localization. The idea is that disorder in the system, combined with interactions among particles, can restrict the way energy and information spread. The particles do not freely explore every possible configuration. They retain a surprising amount of memory about where they started. This allows the periodically driven system to avoid rapidly heating into a featureless state. Disorder sounds as though it should destroy order, which gives the whole arrangement a slightly mischievous quality. But physics often contains situations where one type of disorder protects another type of structure. Random differences between microscopic parts of the system can prevent energy from traveling easily, and that can help preserve the collective rhythm. Many-body localization is not the only way to stabilize time crystalline behavior. Researchers have also explored what are known as pre-thermal time crystals. In these systems, the drive is arranged so that heating happens extremely slowly. The system is not protected forever in the strictest sense, but it can remain in a long-lived organized regime before eventually absorbing enough energy to lose the pattern. For experiments, a state that survives far longer than the relevant observation time can be extremely useful. Physics does not always require forever. It requires a behaviour that is stable enough, well-defined enough, and distinguishable enough to test. This distinction matters because the phrase time crystal can tempt us into asking whether the thing ticks eternally. That is not usually the most useful experimental question. Laboratories operate for finite times. Quantum systems interact with their environment. Control pulses have errors. Measurements have limitations. The realistic question is whether the system displays the expected symmetry breaking behaviour for a sufficiently long period, and whether that behaviour has the robustness expected from a genuine phase. Once the physical platform has been chosen and the interactions are available, researchers must prepare the initial state. In many experiments, this means arranging the quantum spins so that a large fraction begin in a particular orientation. Preparing a quantum system is a little like setting all the pieces on a chessboard before a game, except the pieces are microscopic, the rules are quantum mechanical, and accidentally touching the board would be the least of your problems. Preparation matters because the scientists need a clear starting point from which the repeated dynamics can be measured. They then begin the driving sequence. A pulse changes the spins. The interactions act. Another pulse arrives. The interactions continue. This sequence repeats many times. The researchers do not merely ask whether individual spins are changing. They measure how the collective state evolves from one drive cycle to the next. The key observation is that some property of the system can repeat at a rhythm slower than the drive. If the external sequence repeats after every cycle, while the measured state returns only after every second cycle, the system is displaying what physicists call a sub-harmonic response. The technical term sounds more complicated than the idea. The drive has one basic rhythm. The time crystal responds with a rhythm whose period is a multiple of that basic interval. In the simplest example, the system takes 2 drive cycles to repeat. The laboratory provides 1 beat, while the quantum system settles into a pattern that spans 2 beats. But once again, seeing that 2-beat response is only the beginning. Ordinary systems can also produce subharmonic oscillations. A complicated classical oscillator can respond at half the frequency of a drive. Nonlinear systems can generate all sorts of repeated patterns. If all we were required were a response that repeated every 2 cycles, the definition of a time crystal would become so broad that many familiar machines might accidentally qualify. Researchers therefore test the response more aggressively. They vary the strength of the pulses, they change interaction parameters, they introduce controlled imperfections, they observe whether the subharmonic response remains locked to the same rhythm. If the response frequency simply shifts whenever the drive changes, the behaviour is probably an ordinary dynamical effect. If a region appears in which the collective response remains fixed despite modest changes, that rigidity supports the time crystal interpretation. They also examine how the behaviour changes as interactions are reduced. If the interactions among the particles are crucial, weakening them should eventually destroy the stable temporal order. The system should begin behaving more like a collection of independent components, each accumulating its own errors. This comparison helps demonstrate that the observed rhythm is genuinely a many-body phenomenon. The earliest trapped ion experiments provide a particularly clear picture of this process. Individual ions were held in place using electromagnetic trapping fields. Their quantum states could be manipulated with lasers, and interactions between the ions could be engineered so that the spins influenced one another. Researchers applied a repeating sequence of operations intended to flip the spins and allow them to interact. When the spin flip was deliberately made imperfect, the interacting system still produced a stable response close to twice the period of the external drive. Without sufficient interactions, those imperfections caused the oscillations to drift. With interactions, the collective response became much more rigid. The particles were effectively helping one another maintain the larger temporal pattern. Another early approach used defects inside diamond. Diamond may sound like a more traditional crystal, which creates a slightly amusing situation in which a time crystal, can be created using an ordinary spatial crystal. But the relevant components were not the diamond lattice as a whole. Researchers used particular defects in the material that host controllable quantum spin states. These defects can be manipulated with microwave radiation and observed through their interaction with light. Large numbers of spins can interact with one another inside the diamond. By applying a repeated driving sequence and measuring the response, researchers found signatures of time crystalline behavior in the collective spin dynamics. The experimental platforms were very different. Trapped ions are carefully arranged individual particles held in a controlled vacuum environment. Diamond spin systems involve many quantum defects embedded inside a solid, yet both could display the same broad phenomenon. That is exactly what we expect from a phase of matter. The physical ingredients can differ while the organizing principle remains. More recent experimental approaches have used programmable quantum processors as well. These devices contain arrays of controllable quantum bits, whose interactions can be engineered according to a chosen sequence. A quantum processor is particularly useful for this kind of research because scientists can prepare many body states, apply repeated operations, and measure the behavior of individual components after different numbers of cycles. In such a device, building a time crystal begins to resemble programming a quantum experiment. Researchers design a sequence that produces the required interactions and repeated driving. The quantum bits execute that sequence, while scientists watch how correlations and observables evolve. The hardware may have been developed with quantum computing in mind, but it can also function as a laboratory for unusual phases of quantum matter. This does not mean a time crystal is simply software running on a quantum computer. The important behavior still depends on the physical dynamics of the quantum system. The programmed sequence creates the conditions under which the many-body response can appear. The distinction is similar to using a laboratory furnace to create a new material. The furnace is controlled by humans, but the crystal structure that forms is determined by the physics of the material. Isolation from the environment is another essential ingredient. Quantum states are fragile. Interactions with surrounding particles, stray electromagnetic fields, temperature fluctuations, and imperfect controls can cause decoherence. Decoherence makes the system lose the quantum relationships that researchers are trying to study. The outside world is extremely good at interfering with quantum experiments. Air molecules collide, thermal vibrations occur, electromagnetic noise sneaks into equipment. Even measurement itself has to be handled carefully because quantum measurement is not a completely passive act. Experimentalists therefore go to extraordinary lengths to protect their systems. Trapped ion setups can operate in high vacuum, lasers are stabilized, magnetic fields are controlled, temperatures may be reduced, quantum devices are shielded from environmental noise, timings are calibrated with remarkable precision. All of this effort is needed so that the system has a chance to display its own many-body physics before the environment decides to join the experiment uninvited. Measurement presents its own challenge. A time crystal is defined by behavior across time, which means a single snapshot is not enough. Researchers need to observe the system after many different numbers of drive cycles and reconstruct the repeating pattern. They may repeat the entire experiment many times, stopping after different points in the sequence and measuring the quantum states. This repeated reconstruction allows them to see whether the system alternates reliably. They can examine how long the oscillations survive, how sharply the response is locked to the expected rhythm, how interactions affect the behavior, and what happens when the driving parameters are changed. In other words, scientists do not simply stare at the apparatus until something begins ticking. A large part of the time, crystal exists in the data. The raw experiment produces measurements of spins, correlations, and repeated responses. Researchers then analyze those measurements to determine whether the defining properties of time crystalline order are present. The objects sitting in the laboratory may look completely unchanged to the human eye. This is common in modern physics. A superconductor does not necessarily look strange when you glance at it. A quantum state does not glow merely because it is quantum. Many of the most extraordinary properties of matter reveal themselves only when the correct quantity is measured. So if you walked into a laboratory while a time crystal experiment was running, you might be slightly disappointed. There would probably be cables, computers, vacuum equipment, lasers, microwave electronics, cooling systems, and scientists trying not to touch anything expensive. There would be no transparent object pulsing mysteriously in the middle of the room. The time crystal is the organized behavior of the quantum system. Its defining structure is spread across repeated moments of the experiment. That is what makes building one so different from making an ordinary crystal. To grow an ordinary crystal, you arrange conditions that allow particles to settle into a repeating pattern in space. To create a discrete time crystal, you arrange conditions that allow an interacting quantum system to settle into a repeating pattern in its dynamics. One is recognized by where its components are arranged. The other is recognized by how its state changes and returns. And despite all the advanced equipment involved, the basic recipe is surprisingly easy to summarize in words. Begin with many controllable quantum components, make them interact, prepare them in a known state, apply a repeating drive, prevent heating and environmental noise from immediately destroying the organization. Watch how the collective state responds, then disturb the setup slightly and see whether the strange rhythm refuses to go away. That final test may be the most important part of all. Because if the system behaves differently only when every control has been adjusted to exactly the right value, you may have built a delicate oscillator. If the rhythm survives imperfect pulses, parameter changes, and microscopic disturbances because the many body interactions keep it locked together, then you have something much closer to genuine time, crystalline order. And this leaves us with the misunderstanding that has followed time crystals almost from the moment they were named. We have described systems that can keep repeating a distinctive pattern, sometimes for remarkably long periods, while resisting disturbances that would spoil an ordinary oscillation. It is easy to hear that description and conclude that physicists have somehow found a loophole in thermodynamics, a machine that can move forever without using energy. The experimental reality tells a very different story, because maintaining temporal order and producing unlimited useful work are not the same thing at all, and the difference between them is exactly where the next part of the physics becomes important. The moment someone hears that a time crystal can maintain a repeating pattern for a very long time, one question tends to arrive almost immediately. Has physics finally discovered perpetual motion? It is an understandable reaction. For centuries, inventors have imagined machines that could keep moving forever without fuel, friction, charging, sunlight, heat, or any other source of energy. Now physicists come along describing an exotic state of matter that continues returning to the same pattern, again and again, and the whole thing sounds suspiciously like somebody has found a very sophisticated way around the rules. Fortunately for thermodynamics, and perhaps unfortunately for anyone hoping to power their house with a small container of quantum spins, that is not what a time crystal does. The confusion comes from treating three very different ideas as though they were the same thing. Something can display persistent motion, something can display persistent periodic behavior, and something can continuously provide useful energy. Those statements sound similar in everyday language, but in physics they are not equivalent at all. Consider one of the simplest repeating systems we know, a planet orbiting a star. The Earth has been circling the Sun for billions of years. Every year it returns to approximately the same part of its orbit and begins another trip. If repeated motion automatically meant perpetual motion in the forbidden sense, the solar system would already be breaking thermodynamics rather badly. But the Earth is not generating an endless supply of free energy merely by continuing to orbit. The motion is part of the state of the gravitational system. If we try to extract large amounts of orbital energy and use it to run machines, we change the orbit. The Earth does not politely replace that energy from nowhere. Persistent motion by itself is therefore not the problem. The forbidden machine is one that produces usable energy indefinitely, without receiving energy from anywhere, and without changing some other part of the system in the process. A time crystal is similar in this important respect. The repeated pattern is a property of the system's dynamics. It does not mean that energy is being created each time the pattern repeats. Imagine a collection of quantum spins whose collective state alternates in a stable way under repeated driving. The fact that the pattern keeps returning does not imply that every return releases a fresh packet of energy that can be collected. The system is displaying order. It is not operating as a microscopic power station. This distinction becomes easier to see if we think about a pendulum in an idealized world with no friction. Give the pendulum some initial energy, and it could swing back and forth indefinitely. At the highest point, more of its energy is associated with position. As it falls, that energy becomes motion. As it rises on the other side, the energy changes form again. Nothing needs to be created during each swing. The same energy is being redistributed within the system. In the real world, air resistance and friction gradually convert some of that organized mechanical energy into heat, so the pendulum slows down. But the ideal case is perfectly compatible with energy conservation. Endless repetition is not automatically endless energy production. Quantum physics contains many similarly persistent processes. An isolated quantum system can maintain a state or an oscillatory relationship for a long time without continuously generating new energy. The important question is where the energy comes from, where it goes, and whether useful work can be extracted without changing the system. Thermodynamics cares about those questions, not about whether something happens to repeat. The discrete time crystals we've been discussing make the situation even clearer because they are usually driven systems. Researchers apply a repeating sequence of pulses or controlled operations. The drive is external. The system is therefore not sealed away from everything while mysteriously creating a rhythm from nothing. Experimental equipment is actively manipulating it. Lasers may be firing, microwave fields may be applied, quantum gates may be executed. The laboratory is doing work to establish the conditions under which the time crystalline response can appear. This does not mean the external drive directly programs the entire time crystal pattern. As we have seen, that would miss the interesting part. The drive supplies a basic rhythm, while the interacting many-body system develops a response that repeats over a larger interval. The symmetry breaking belongs to the collective state, but the presence of a drive means there is no reason to imagine that the system is energetically independent of its surroundings. Imagine a group of dancers performing in a room while a drummer provides a steady beat. The dancers organize themselves into a pattern that repeats only after every second drum beat. Their larger rhythm is not explicitly contained in each individual beat, so there is real organization happening within the group. But nobody would claim the dancers have discovered an infinite source of energy because their pattern lasts for a long time. The drummer is still playing, the dancers are still using energy, and the interesting phenomenon is the organization of their response, rather than the creation of free power. Time crystals are obviously not people dancing, but the same separation is useful. The surprising physics is in the relationship between the external timing and the collective response. The system establishes temporal order. Thermodynamics is not being asked to hand out free electricity. There is another reason the perpetual motion idea can be misleading. In everyday machines, motion is often valuable because we can connect it to something else. A rotating turbine can drive a generator. A moving piston can turn a shaft. Water flowing downhill can produce electricity. So when we hear that something keeps moving, we naturally imagine attaching a tiny generator and collecting energy forever. But extracting work changes physical systems. Suppose you have a perfectly spinning wheel in an ideal frictionless environment. The wheel could keep rotating for an extremely long time if nothing disturbed it. Now connect the wheel to a generator and begin extracting electrical energy. The wheel slows because the generator takes energy from its motion. To keep the wheel turning at the same speed, you must replace that energy from somewhere else. A time crystal does not avoid this logic. If you couple strongly to the system, and try to extract useful work from its repeating behavior, that coupling becomes part of the physical situation. You disturb the state. The temporal order is not an unlimited bank account from which energy can be withdrawn without consequence. In fact, one of the greatest challenges in creating time crystalline behavior is almost the opposite of generating energy. Researchers often struggle to stop the system from absorbing too much energy. A periodically driven many-body system is repeatedly exposed to an external influence. Ordinarily, such a system can absorb energy from the drive and heat up. The particles begin exploring more and more possible states. The carefully organized behavior can disappear as energy spreads throughout the system. Instead of maintaining a sharp repeating pattern, the system gradually approaches a much less interesting state in which the original structure has been washed away. If time crystals were magical perpetual motion machines, scientists would be worrying about how to extract all the limitless energy pouring out of them. In reality, they often worry about precisely the reverse problem, preventing unwanted energy absorption from destroying the temporal order. This is why ideas such as localization and pre-thermalization became so important. The time crystal needs a way to avoid ordinary heating for long enough that the ordered response remains visible. In some models, disorder and interactions restrict how energy spreads. In other situations, the drive is chosen so that heating occurs only very slowly. Either way, the goal is not to obtain energy from nowhere. The goal is to stop the system from turning the externally supplied energy into featureless heat too quickly. There is something almost amusing about this once you notice it. The popular misunderstanding says that a time crystal produces unlimited energy. The experimental problem says that a time crystal must be protected from absorbing too much energy. Thermodynamics has not been defeated. It is standing in the middle of the laboratory, making everyone's life more complicated, exactly as usual. The original proposal for time crystals helped create some of this confusion because it involved the idea of a ground state displaying periodic behavior. A ground state is the lowest energy state available to a system. If something could sit in that state while continuing to perform observable motion, it was tempting to imagine that the motion might continue forever without an energy source. But even the original proposal was not intended as a machine for producing unlimited useful work. The goal was to explore spontaneous symmetry breaking in time. More importantly, the simplest form of the proposed equilibrium time crystal was later shown not to work under broad ordinary conditions. The versions that became experimentally established moved into non-equilibrium physics, where repeated driving plays an important role. So the modern time crystal does not rely on a loophole that allows a ground state to behave like an eternal motor. The successful idea is different. The system is driven, its components interact, and the resulting many-body state can break the discrete time translation symmetry of the drive. Thermodynamics remains perfectly comfortable with this. It may help to remember what the laws of thermodynamics actually forbid. The first law concerns energy conservation. Energy cannot simply appear from nowhere. It can move between systems and change form, but if you want useful energy to come out of a device, the accounting has to work. A time crystal does not provide an exception. The second law deals with the direction in which energy transformations naturally proceed, and with the growth of entropy in isolated macroscopic systems. It tells us why many processes are effectively irreversible. Heat flows from hotter objects toward colder ones under ordinary conditions. Gas spreads through a room rather than spontaneously collecting itself into one corner. A broken cup does not reassemble itself from scattered pieces while politely jumping back onto the table. A time crystal does not reverse these tendencies either. The ordered temporal response can survive because the system is in a special non-equilibrium regime. That is very different from saying entropy has been abolished. There are many examples in physics where local or temporary order exists without violating the second law. A refrigerator creates a cold, ordered environment inside by consuming electrical energy and releasing heat elsewhere. Living organisms maintain enormously complex internal organization by taking in energy and releasing waste heat. A snowflake forms an elegant ordered structure, while the total thermodynamic process remains consistent with increasing entropy. Order by itself does not violate thermodynamics. Time order does not violate it either. The interesting feature of a time crystal is that the order concerns repeated behavior rather than only a spatial arrangement. But the universe does not suddenly become exempt from energy conservation, because the pattern is temporal. There is another useful comparison with ordinary crystals. A diamond can maintain its atomic structure for an extremely long time. The atoms remain arranged in an ordered lattice. Nobody expects the diamond to provide endless energy merely because the pattern persists. Stability is not fuel. A time crystal replaces stable spatial order with stable temporal order. The persistence of the pattern is what makes it crystal-like. That persistence should not be confused with an ability to continuously do work. Suppose an ordinary crystal sits on your desk for 100 years. Its lattice may remain largely intact. The pattern has survived, but the crystal has not powered your lamp during those 100 years. A time crystal can similarly maintain an ordered pattern in its dynamics without providing a stream of energy that can be harvested. This is why the phrase perpetual motion needs to be handled carefully. There are different senses in which something might continue indefinitely. A mathematical model can contain oscillations that never decay. An isolated quantum system can preserve coherent dynamics under ideal conditions. An astronomical system can continue moving for billions of years. None of these automatically qualifies as a forbidden perpetual motion machine. The forbidden part appears when someone claims that useful work can be extracted forever without an energy source or without producing the compensating changes required by thermodynamics. Time crystals make no such promise. In real experiments, their behavior is also not literally eternal. Quantum systems are never perfectly isolated. Environmental noise causes decoherence. Control pulses are imperfect. Interactions with surrounding matter gradually affect the state. Some types of time crystalline behavior are long-lived rather than infinitely long-lived. Pre-thermal time crystals, for example, can maintain their characteristic response for a very long interval before eventual heating destroys it. This does not make the phenomenon less meaningful. Plenty of phases and physical effects are studied over finite times. A material does not need to remain unchanged until the end of the universe before physicists are allowed to describe its properties. What matters is whether the behavior lasts far longer than the microscopic timescales that would normally destroy it, whether it shows the expected rigidity, and whether it appears across a suitable range of conditions. The word crystal again helps us understand the standard being used. An ordinary crystal is never mathematically perfect. It contains defects. It experiences thermal vibrations. It can crack, melt, dissolve, or react chemically. Yet crystalline order remains a perfectly meaningful physical concept. A time crystal can similarly be imperfect and finite while still possessing genuine temporal order. There is also no requirement that every part of the system move continuously. The repeating observable might be a pattern in quantum spin orientations or correlations. That matters because perpetual motion machines usually evoke mechanical images. Wheels spinning, magnets rotating, pistons cycling, perhaps accompanied by an inventor explaining why everyone else has misunderstood the second law. A time crystal may contain no obvious macroscopic movement at all. Nothing visible has to rotate. Nothing needs to travel around a track. The repeated quantity can be a quantum property that is detectable only through carefully designed measurements. Calling this motion is not necessarily wrong in a broad sense, because the state evolves through time, but it is very different from a motor turning a shaft. The confusion becomes even easier to avoid when we separate energy from frequency. A system can have a very precise repeating frequency without creating energy. Your phone receives electromagnetic signals at precise frequencies every day. A quartz watch maintains a regular oscillation. An atom can interact with light at highly specific frequencies. frequency tells us how often a pattern repeats. It does not tell us that energy is being generated. A time crystal is fundamentally interesting because of the frequency relationship between the drive and the system's collective response. If the drive repeats every cycle, and the time crystal repeats after 2 cycles, that locked relationship reveals broken discrete time translation symmetry. The scientific information is in the timing. It would be rather like discovering an orchestra that, despite receiving the same conducting signal on every beat, organizes itself so that the complete musical pattern repeats every second beat and remains locked into that pattern, even when the conductor makes small timing mistakes. The fascinating part would be the collective organization. Nobody would conclude that the orchestra was creating infinite calories for the musicians. Once perpetual motion is removed from the picture, we can see why time crystals are scientifically interesting for a much better reason. They show that a driven many-body system can possess stable order in a place where we did not traditionally look for phases of matter. For much of physics, phases were understood through equilibrium. A system was allowed to settle down. Its temperature, pressure, magnetic environment, and other conditions determined the state it preferred. Water froze, magnets aligned, materials became superconducting. Driven systems seemed less tidy. They were being constantly disturbed, so we might expect complicated transient behavior rather than stable phases. Time crystals helped demonstrate that this expectation was too limited. Systems far from ordinary equilibrium can also organize themselves into robust patterns. That lesson reaches beyond time crystals. It suggests that there may be many forms of matter whose defining properties appear only when a system is continually driven, interacting, and prevented from simply thermalizing. Instead of asking only what matter becomes when we leave it alone, physicists can ask what kinds of order become possible when matter is kept in controlled motion. This is a major conceptual shift. A time crystal is therefore not important because it breaks thermodynamics. It is important because it obeys thermodynamics while still doing something our older classification of matter did not prepare us to expect. The laws remain intact. Energy remains conserved. Entropy remains relevant. Heating remains a problem. Environmental noise remains irritating. Experimental equipment remains expensive. And yet, within all those restrictions, quantum matter manages to create a stable pattern in time. There is something more interesting about that than a loophole would have been. A loophole would simply tell us that one of our old rules was wrong. Time crystals tell us that the old rules allow more possibilities than we'd realized. This happens surprisingly often in physics. The universe does not need to break its laws to surprise us. It only needs to explore parts of those laws we had not thought carefully enough about. Superconductors do not violate electrical physics when they carry current without ordinary resistance. They reveal a collective quantum state in which electrical behavior changes dramatically. Superfluids do not break mechanics when they flow in unusual ways. They reveal another form of collective quantum order. Time crystals belong to this tradition. Their behavior looks impossible only when we try to understand them using the wrong category. If we imagine them as machines, we start asking where the fuel comes from. If we imagine them as phases of matter, we start asking the better question. What is being ordered? The answer is the system's behavior through time. That is the real achievement. Many quantum components interact so that the system develops a stable temporal structure. The response can remain locked to a characteristic rhythm. It can resist small imperfections. It can reveal spontaneous breaking of a symmetry associated with the repeated drive. None of those statements requires free energy, and none requires physics to apologize to thermodynamics. In fact, the need to protect the time crystal from heating shows how deeply thermodynamics remains involved. The system lives near a boundary between order and thermalization. If energy spreads too freely, the temporal pattern disappears. If interactions, driving, and isolation are arranged appropriately, the system can maintain that pattern for a long time. That tension gives time crystals much of their scientific value. They provide a laboratory for asking how quantum systems remember, how they lose information, how interactions create collective behavior, and how ordered phases survive far from equilibrium. The strange ticking is therefore only the visible clue. Underneath it lies a much larger question about quantum matter. Ordinary intuition tells us that if we keep disturbing a system, eventually it should forget its original structure. Push it, shake it, drive it, and sooner or later the motion should become messy and thermal. Yet a time crystal can retain a remarkably precise temporal pattern, despite being repeatedly driven. Why does the system remember that rhythm? How do interactions preserve it? What does this tell us about information spreading through quantum matter? And how many other forms of non-equilibrium order might be hiding in physical systems that researchers have only recently learned how to control? Those questions take us away from the tempting fantasy of an endless energy machine and towards something far more useful. Time crystals are not a way to escape the laws of physics. They're a way to discover just how much strange behavior those laws already permit, especially when many quantum particles begin acting together. Once the idea of perpetual motion is set aside, time crystals become interesting for a much better reason. They give physicists a way to study how large collections of quantum objects can organize themselves when they are repeatedly disturbed and prevented from settling into an ordinary equilibrium state. That may sound like a very specialized problem, but it touches several of the deepest questions in modern quantum physics. How does a complex quantum system remember its past? Why do some patterns survive while others disappear? What happens when thousands or millions of microscopic components interact at once? How does a quantum system move from an organized state towards something that looks thermal and ordinary? And can stable phases of matter exist even when the system is constantly being driven, rather than quietly left alone? Time crystals do not answer all of these questions, of course, but they provide a remarkably clean place to ask them because their defining feature is easy to state. A repeated external drive is applied, and the many-body system develops a stable response with a different repeating rhythm. If that rhythm survives disturbances that should ruin a simple oscillator, then something collective is holding the pattern together. This matters because quantum mechanics becomes dramatically more difficult when many particles interact. A single quantum object can already behave in ways that do not resemble ordinary experience, but at least we can describe its possible states without immediately needing a small army of computers. Add a second object and the possibilities multiply. Add many more and the number of possible configurations grows extraordinarily quickly. At that point, the system cannot usually be understood by imagining that every particle simply has its own independent little story. The particles influence one another, become correlated, exchange information, and collectively produce behavior that may not be obvious from any one component. Time crystalline order is a clear example of this. No individual spin contains the entire pattern. The interesting rhythm belongs to the interacting system. This is part of a much larger lesson that appears throughout condensed matter physics. Matter can possess properties that are not meaningful when we look at the microscopic pieces one at a time. A single molecule is not a liquid. One atom does not have a melting point. One electron cannot create a conventional superconducting phase by itself. Collective organization changes what the system is capable of doing. Time crystals extend this familiar idea into dynamics. Instead of asking only how particles organize themselves across space, physicists ask how they organize their behavior across repeated moments. The result is a phase whose identity depends not just on what the system is, but on how the system repeatedly evolves. That alone changes the traditional picture of a phase of matter. Most of the phases people first learn about are equilibrium phases. Place water under suitable conditions and it becomes ice. Heat it, and the crystal melts. Increase the temperature further and eventually the liquid becomes vapor. These states can be understood by imagining matter settling into the form that is appropriate for its temperature, pressure, and other environmental conditions. The system is allowed to relax, Given enough time, it approaches equilibrium. A time crystal lives in a different situation. It is repeatedly driven. Something keeps happening to the system, so it is never simply allowed to settle into ordinary equilibrium. Older intuition might suggest that such a system should eventually become uninteresting. Continue disturbing a complicated collection of particles and energy should spread throughout it. The system should heat, lose detailed memory of its starting state, and gradually forget the carefully arranged pattern that researchers created. That expectation is often correct. In fact, it is one of the main reasons time crystals are difficult to produce. Yet under certain conditions, the many-body system can resist that ordinary fate long enough to support a stable, temporal pattern. This resistance teaches physicists about thermalization, which is the process through which a complex system loses detailed information about its initial condition and begins behaving like a thermal state. Thermalization is so familiar in everyday life that we rarely notice how deep the question actually is. Pour hot water into cooler water, and eventually you get water at a more uniform temperature. Place a drop of dye in a glass, and the dye spreads rather than remaining concentrated forever in one neat little blob. In large systems, energy and information tend to spread. The fine details of the initial arrangement become increasingly difficult to recover. Quantum mechanics is supposed to describe the microscopic rules underneath all of this. But those microscopic rules can preserve information in ways that make the emergence of ordinary thermal behavior surprisingly subtle. Time crystal research sits directly inside that puzzle. If a quantum system continues displaying a precise repeating response after many drive cycles, then it has retained some form of structured memory. It has not completely forgotten how its components are organized. That does not mean the system stores a memory in the same way that a computer stores a photograph. The word memory here describes the persistence of information about the system's state and its repeating pattern. If every part of the system quickly lost all connection with the earlier cycles, there would be no reason for a rigid temporal response to survive. The fact that the system continues returning to a characteristic pattern tells researchers that interactions and constraints are preventing ordinary thermalization from erasing everything. This is one reason many body localization became so important in the early theory of discrete time crystals. In a localized system, disorder can prevent particles from freely spreading information and energy through the entire material. The components still interact, but the system does not rapidly explore all of the configurations that an ordinary thermalizing system would. It can retain unusually strong memory of where it started. Normally, disorder sounds like the enemy of a crystal. If you're trying to build a neat spatial pattern, random imperfections seem like something you would want to remove. Yet in some time crystal models, disorder helps protect the temporal order. The random environment prevents the quantum system from freely absorbing and redistributing energy, which can allow the repeated pattern to survive. It is one of those lovely reversals physics occasionally gives us. A certain amount of microscopic mess can help preserve a larger kind of order. Time crystal research has also shown that localization is not the only possible route. Another important idea is pre-thermalization. A pre-thermal system is not protected from heating forever, but it can remain in a long-lived organized regime before eventually reaching a fully heated state. If the external drive operates in an appropriate range, the system can behave for a very long time as though it has settled into a temporary effective phase. During that interval, time crystalline order can appear. The word temporary might sound disappointing after all the excitement surrounding time crystals, but physicists are not usually disappointed by a stable state lasting vastly longer than the microscopic processes that would normally destroy it. Nature is filled with useful phenomena that are not eternal. Stars are not eternal. Atoms in excited states are not eternal. Ordinary crystals can melt. Magnets can lose their magnetization. A phase does not need to survive until the universe ends in order to reveal real physics. Pre-thermal time crystals are especially interesting because they suggest that temporal order can emerge through more than one microscopic mechanism. That is exactly what we hope for when identifying a genuine physical principle. If the phenomenon appeared only in one very specific laboratory arrangement, it might be an unusual trick of that particular device. When related forms of temporal order appear across different systems and through different stabilizing mechanisms, the idea begins to look much more general. There is another lesson hiding in the way time crystals respond to imperfections. Quantum systems are famously fragile. Small unwanted interactions with the environment can cause decoherence. Tiny errors can accumulate. This is one of the central difficulties in building quantum computers, where researchers need to control quantum states precisely enough to perform useful calculations before noise destroys the information. Time crystals show that certain many-body behaviors can possess a surprising kind of robustness. The repeated response does not require every individual component to behave perfectly. Interactions within the system can lock the collective dynamics into a stable pattern, even when the driving pulse contains small errors. One particle may be slightly mistimed, but the many-body state can still maintain the larger rhythm. That does not mean time crystals provide an easy solution to quantum error correction. It would be misleading to imagine that scientists can simply turn every quantum computer into a time crystal and watch all the errors disappear. The requirements and goals are different. Still, the broader principle is valuable. Collective quantum phases can protect particular patterns of behavior against certain disturbances. Understanding how that protection works may help researchers learn more about building quantum systems that remain useful despite imperfect control. This is one reason programmable quantum processors have become interesting platforms for time crystal experiments. A quantum processor contains many controllable quantum bits. Researchers can prepare the bits, engineer interactions, apply repeated operations, and measure how the system changes over many cycles. Instead of using the processor only to perform a calculation, scientists can use it as a laboratory for quantum matter. This is a fairly remarkable shift in how we think about computers. An ordinary computer can simulate a physical system by calculating what the equations predict. A programmable quantum device can sometimes do something more direct. Its own quantum components can be arranged so that their behavior represents the many-body physics being studied. The processor becomes part calculator and part experimental material. Time crystals have therefore become examples of what quantum simulation can reveal. Researchers can create a controlled model of an interacting quantum system, watch temporal order emerge, deliberately introduce imperfections, and test how long the pattern survives. The experiment becomes a way of asking nature a very specific question about collective quantum behavior. The subject also sharpens our understanding of symmetry. Before time crystals, spontaneous symmetry breaking was already one of the central organizing principles in modern physics. It helps explain crystals, magnets, superconductors, and many other phases. But time crystals show that symmetry breaking does not need to be restricted to static arrangements. A system can break a symmetry associated with its dynamics. That may sound like a small extension, but conceptually it is significant. For a long time, phases of matter were classified largely by asking what symmetries their stable states possessed. Time crystalline phases force us to think about patterns in evolution as well. Matter can be organized not merely by the arrangement of its components, but by the repeated sequence of states those components move through. This leads naturally into the broader field of non-equilibrium phases of matter. A time crystal is one example, but the larger message is that driven quantum systems can contain forms of order that have no simple equilibrium counterpart. If researchers can classify these phases, they may discover a much richer landscape of quantum behavior than the traditional solid, liquid, magnetic, and superconducting examples suggest. Imagine how narrow our description of ordinary matter would be if we only classified objects by their chemical ingredients. A diamond and graphite are both built from carbon, yet their properties are dramatically different because the atoms are organized differently. Structure matters. In the same way, two quantum systems made from similar microscopic components can behave very differently depending on how they are driven, and how their dynamics are organized through time. Time therefore becomes part of the classification. Not time as a substance, and not time as something being turned into matter, but time as part of the pattern used to describe the phase. Another important lesson concerns the distinction between individual behavior and collective behavior. Human intuition often tries to explain a complex system by finding one object that is responsible. If a clock ticks, we look for the pendulum or vibrating crystal. If a machine moves, we look for the motor. If a light flashes, we look for the circuit controlling it. A time crystal resists that kind of explanation. There is no single tiny component acting as the master clock. The stable temporal order emerges because many components interact. Remove those interactions and the rigidity can disappear. The system begins behaving like independent oscillators, and small errors cause the pattern to drift. This is a powerful demonstration of emergence, one of the most important ideas in physics. Emergence describes situations where the behavior of a large system cannot be usefully summarized by simply listing the properties of its pieces. The interactions create something new at the collective level. Temperature is emergent, pressure is emergent, many forms of magnetism are emergent, superconductivity is emergent, time crystalline order is another example, and because it is temporal order, it gives researchers a particularly clear way to study how emergence develops during repeated quantum evolution. They can watch the pattern strengthen, weaken, or disappear as interactions and driving conditions change. They can deliberately move the system from one dynamical regime to another and see what happens to the temporal response. This brings us to the idea of phase transitions. In ordinary matter, a phase transition occurs when changing a condition causes the system to reorganize. Cool water and it freezes. Heat a magnet enough and its ordered magnetic state can disappear. In driven quantum systems, researchers can also observe transitions between regimes with and without time crystalline order. Adjust the strength of interactions, change the disorder, alter the driving conditions, or increase the effects that cause thermalization, and the stable temporal pattern can eventually break down. The system crosses from a regime where the larger repeating rhythm is protected into one where it is not. Studying where and how that happens helps physicists understand what ingredients are genuinely responsible for the time crystal. It is one thing to observe an oscillation. It is much more informative to map out the conditions under which the oscillation becomes a robust collective phase and the conditions under which that phase disappears. Time crystals also provide a useful test of how information spreads through quantum systems. In a strongly interacting many-body system, a disturbance introduced in one location can influence increasingly distant parts of the system. Correlations spread. Quantum information becomes distributed across many components. This process is related to thermalization and to the growth of entanglement. Entanglement is one of the most famously strange features of quantum mechanics. Two or more quantum objects can share a state in such a way that their properties cannot be described independently. In many body systems, networks of these quantum correlations can become extremely complicated. Time crystalline behavior does not reduce to entanglement alone, but studying the way correlations evolve can help researchers understand why the temporal order survives. The system's repeated response is supported by relationships between components, not merely by the behavior of isolated particles. That makes time crystals part of a broader effort to understand quantum information as something physical. Information is not floating above the experiment as an abstract concept. It is encoded in the state of matter, in correlations between particles, and in the way those correlations change through time. When a time crystal maintains its rhythm, it demonstrates that certain information about the collective state remains organized despite repeated disturbance. When the time crystal melts into a thermal state, that organization is lost. The word melt is occasionally used by physicists when discussing the disappearance of ordered phases, even when nothing becomes a liquid. It is a useful reminder that the concept of a phase is broader than the everyday categories of solid and liquid. A time crystal can lose its temporal order in a way that resembles the loss of spatial order when an ordinary crystal melts. This comparison gives us a useful picture of what time crystals reveal. An ordinary crystal tells us that particles can organize their positions. A magnet tells us that microscopic magnetic properties can organize their orientations. A superconductor tells us that quantum particles can coordinate in a way that dramatically changes electrical behavior. A time crystal tells us that many body quantum systems can organize the rhythm of their evolution. That rhythm is not decorative. It reflects a genuine structural property of the state. There are also practical reasons physicists care about long-lived, robust quantum dynamics. Quantum technologies depend on controlling systems that would often prefer to interact with their environment and lose the carefully prepared quantum information. Any phenomenon that teaches us how interactions can stabilize behavior, suppress unwanted heating, preserve correlations, or create predictable dynamics is potentially valuable. It is still much too early to treat time crystals as a ready-made technological component. They are primarily research systems. Headlines sometimes leap directly from an interesting quantum phase to futuristic clocks, memory devices, sensors, or quantum computers, but laboratory physics is rarely that immediate. Discovering a new kind of order and turning it into a useful device are very different tasks. The more realistic value at the moment is scientific. Time crystals give researchers another controlled setting in which to study coherence, many-body interactions, driven dynamics, thermalization, and the boundaries between stable quantum order and chaotic heating. They also demonstrate how much modern physics depends on control. Many exotic quantum phases are not objects we simply stumble across while walking through the countryside. They appear because experimentalists have learned how to manipulate matter with extraordinary precision. Individual ions can be trapped, spins can be addressed, microwave pulses can be timed, quantum processors can be programmed. Measurements can be repeated thousands of times. As experimental control improves, physicists are able to explore states of matter that may be extremely rare or absent under ordinary natural conditions. That changes the question from asking only what kinds of matter nature happens to provide around us, to asking what kinds of matter the laws of quantum physics allow when we deliberately create the right conditions. Time crystals are a striking answer. They say that the laws allow a system to possess stable order in its repeated evolution. They say that many body interactions can create temporal rigidity. They say that driven quantum systems need not immediately dissolve into thermal disorder. They say that phases of matter can be defined partly by how states return through time. Perhaps the most important lesson is that the quantum world is not strange, only because individual particles behave strangely. The deeper strangeness often appears when many quantum objects cooperate. A single particle can surprise us with superposition or uncertainty, but a many-body system can produce entirely new forms of order that were not obvious from the microscopic rules alone. Time crystals belong to that second kind of quantum strangeness. Nothing supernatural is happening. No law of physics is being violated. Time itself has not begun crystallizing into little solid pieces. The particles are simply following quantum mechanics, interacting with one another and responding to a repeated drive. Yet from those ordinary ingredients, at least ordinary by quantum standards, a new organized rhythm emerges. This is a recurring pattern in modern physics. The rules can be simple to state, while their collective consequences are astonishingly rich. Understanding an electron does not automatically tell you everything a solid can do. Understanding a water molecule does not immediately give you snowflakes, waves, ice, and turbulence. Understanding one quantum spin does not automatically reveal time crystalline order. The interesting behavior lives in the relationships, and those relationships may be why time crystals are more useful as a scientific idea than their dramatic name first suggests. They give us a controlled example of how order can appear in a system that is never truly at rest, how quantum information can resist being washed away, and how matter can develop patterns not just in where things are, but in when particular collective states return. By now, the phrase time crystal should therefore sound much less mysterious than it did at the beginning. We know that it is not a crystal made from time. We know that it is not a clock hidden inside a material. We know that it does not create free energy and does not provide a shortcut to perpetual motion. We know that the important ingredients are repeated driving, many body interactions, robust temporal order, and the breaking of a time translation symmetry. What remains is to bring those ideas together without hiding behind the terminology. Because after all the trapped ions, quantum spins, broken symmetries, heating problems, and many body interactions, there is still one very simple question waiting underneath everything we have discussed. When physicists use this strange name, what is a time crystal really? After everything we have explored, from ordinary crystals and broken symmetries to trapped ions, quantum spins, repeated driving, thermalization, and the rather persistent myth of perpetual motion, we can finally return to the question that brought us here in the first place. What is a time crystal really? The simplest answer is that a time crystal is a physical system whose collective behavior forms a stable repeating pattern in time, in a way that is closely related to how an ordinary crystal forms a repeating pattern in space. That sentence is accurate, but by itself it still leaves plenty of room for confusion, because almost everything around us seems to repeat in time if we wait long enough. Clocks tick, hearts beat, planets orbit, washing machines spin. Your neighbour may begin drilling into a wall at almost exactly the same inconvenient hour every weekend. Repetition is everywhere, and repetition alone is not enough. What makes a time crystal special is the way the repeating behaviour emerges from an interacting many-body system, and the way that behaviour breaks a symmetry in the timing of the system. An ordinary crystal gives us the clearest comparison. Inside a crystal, atoms arrange themselves into a repeating pattern. The fundamental laws do not mark one microscopic position as special, but the crystal that formed selects a regular set of positions. Move through the material by the correct distance and the pattern repeats. That is why physicists describe an ordinary crystal in terms of spatial order and broken spatial translation symmetry. A time crystal extends the same basic logic into dynamics. Instead of asking how the system repeats when we move from one place to another, we ask how its state repeats as we move from one moment to another. In the most familiar experimental version, the system is driven by an external sequence that repeats regularly. Every cycle of that drive is supposed to be equivalent. Yet the quantum system can organize itself so that its full response repeats only after several drive cycles. The conditions repeat with one rhythm, while the state chooses a larger rhythm. That difference is the essential clue. Imagine a drummer tapping at a steady pace while a group of dancers responds. If the dancers perform exactly the same movement on every beat, they are simply following the drummer. Now suppose the drummer keeps tapping the same beat, but the dancers settle into a stable pattern that takes 2 beats to complete. On one beat they take one configuration, on the next they take another, and only on the following beat do they return to the first. The drummer has not changed the instructions from one beat to the next. The larger pattern belongs to the group. If the dancers remain locked into that 2-beat pattern, even when the drummer makes small mistakes, the behaviour becomes more interesting still. The group has developed a kind of collective timing that is more stable than the individual pushes creating it. A discrete time crystal behaves in an analogous way, although the dancers are quantum degrees of freedom, and the choreography is governed by many body physics rather than someone counting quietly at the back of a rehearsal room. This is why a time crystal is not simply a clock. A clock is deliberately engineered so that some component oscillates with a chosen period. A quartz watch uses a regular vibration. A pendulum clock relies on a swinging pendulum. An atomic clock uses an extremely precise atomic transition. These are wonderful devices, but their repetition is the mechanism we designed them to have. A time crystal is interesting for a different reason. The external drive provides a basic repeated schedule, yet the many-body system develops additional temporal structure through its own collective interactions. The larger rhythm is not simply written directly into every pulse, it emerges as an ordered response. The word collective is doing a great deal of work here. A time crystal is not about one isolated particle behaving strangely. Quantum mechanics already gives individual particles enough opportunities for strange behavior without needing a new name. The important physics appears when many quantum components influence one another. Their interactions can lock the system into a shared temporal pattern, and that pattern can resist small imperfections. One component may be slightly disturbed, one pulse may be slightly inaccurate, yet the many-body response can remain stable because the order belongs to the system as a whole. This rigidity is one of the reasons physicists take time crystalline behavior seriously as a phase of matter rather than a curious oscillation. If you tune an ordinary oscillator very carefully, you can produce all sorts of repeated responses. Change the tuning slightly, and the response changes. That is not surprising. A genuine phase should have some robustness. Ice does not stop being ice because one molecule is misplaced. A magnet does not immediately lose all magnetic order because one microscopic component is disturbed. In a related way, time crystalline order can survive modest changes in the driving conditions. The characteristic rhythm remains locked over a range of parameters. That is the part that makes the word crystal more than a dramatic label. Ordinary crystals are defined by organized repetition and rigidity in space. Time crystals display organized repetition and rigidity in time. The analogy is not perfect, because space and time play different roles in quantum theory, but the connection through symmetry breaking is real. It is also important to remember that a time crystal does not mean that time itself has turned into a crystal. There are no tiny blocks of yesterday arranged beside tiny blocks of tomorrow. Nothing has become solidified in the fourth dimension. The word time describes where the repeating order appears. The physical system still exists in ordinary space. It may be a chain of ions, a collection of spins inside a material, or a programmable array of quantum bits. The unusual part is the sequence of states the system moves through. Nor does the time crystal need to look unusual. If you walked into a laboratory where one was being studied, you would probably see equipment rather than a glowing object. There might be vacuum chambers, lasers, microwave electronics, cables, cryogenic systems, computers, and researchers trying to remember which cable nobody is supposed to touch. The time crystal itself would be revealed through measurements. Scientists would prepare the system, apply repeated operations, measure the state after different numbers of cycles, and reconstruct the temporal pattern from the data. That can feel slightly disappointing if the phrase time crystal gave you visions of a luminous object humming quietly in a glass case, but the reality is much richer. Modern physics often studies properties that are invisible to ordinary sight. You cannot look at a superconductor and immediately see its quantum state. You cannot stare at two particles and visually inspect their entanglement. The most important properties of matter are often hidden in how systems respond when we ask the right experimental question. Time crystals answer one such question. Can a quantum many-body system form stable order in its dynamics? The answer is yes, under the right conditions. Those conditions matter. The modern discrete time crystals that have been experimentally realized are generally not systems sitting quietly in their lowest energy state. They are driven systems. Researchers repeatedly manipulate them. This distinction emerged from the unusual history of the idea. The earliest proposals asked whether a system could spontaneously oscillate in equilibrium while remaining in its ground state. That more ambitious version encountered powerful theoretical objections. The simple equilibrium time crystal did not survive. But the underlying idea of temporal symmetry breaking did survive. Researchers shifted their attention to systems that are periodically driven, and therefore live outside ordinary equilibrium. Once they made that change, the theory became much more promising. A repeated drive already provides a discrete timing structure, and the many-body system can break that remaining symmetry by responding with a longer period. The impossible version of the idea gave way to a different version that could actually be built. That history is worth remembering because it shows something important about how science develops. A failed proposal is not always wasted effort. Sometimes it identifies exactly where the real physics is hiding. The first idea asked too much from an equilibrium system. The objections revealed the limit. Researchers then asked whether temporal order could appear somewhere beyond that limit, and the answer led into non-equilibrium quantum matter. This is where time crystals become more than a curious addition to the list of exotic phases. They reveal that driven systems can have stable forms of order. That was not always an obvious thing to expect. If you repeatedly disturb a complex system, common intuition suggests that the disturbance should eventually ruin whatever organization was present. Energy spreads. The system heats. Information about its initial state becomes harder to recover. Everything gradually moves toward a thermal state, where the detailed pattern has disappeared. Time crystals show that this is not the only possibility. Under suitable conditions, interactions, disorder, or long-lived prethermal behavior can prevent the system from immediately losing its temporal structure. The repeated response remains organized for a remarkably long time. The system continues distinguishing between different parts of the driving sequence, even though the external drive treats each cycle as equivalent. In that sense, a time crystal is also a demonstration of memory. Not memory in the sense of remembering a childhood holiday or where you put your keys, but physical memory. The system retains information about the structure of its earlier states and uses that information through interactions to maintain a repeated collective pattern. This is closely connected to one of the central questions of many-body quantum physics. How does an isolated quantum system eventually begin looking thermal? The microscopic laws preserve quantum information in subtle ways, yet large systems often behave as though the fine details have been forgotten. Time crystals give researchers a controlled example of a system that resists that forgetting. They also show us that disorder can play a surprisingly constructive role. In some early models, random differences within the system helped prevent energy from spreading too freely. Disorder, which normally sounds like the opposite of a crystal, could help protect time crystalline order. Physics is quite fond of these little reversals. Just when a word appears to have one clear meaning, the equations quietly remind us that context matters. And then there is the question of energy, because no explanation of time crystals is complete until the perpetual motion machine has been gently removed from the room. A time crystal does not produce unlimited energy. It does not violate energy conservation. It does not overturn thermodynamics. It cannot be connected to a generator and persuaded to supply free electricity forever. The reason is straightforward. Repeating behavior is not the same as producing useful work. A system can return to similar states again and again without creating energy. A perfectly isolated oscillator can continue oscillating while conserving the energy it already has. An orbit can persist for an enormous time without generating a fresh supply of energy during every revolution. The repetition describes the state of the system, not a magical energy source. In driven time crystals, the misunderstanding becomes even less plausible because the system is being externally manipulated. The laboratory provides the repeated drive. Lasers, microwave fields, or quantum control operations are doing something to the system. The interesting result is not that the time crystal provides energy without input. The interesting result is that its collective response becomes organized into a rhythm that differs from the rhythm of the drive. Trying to extract useful work would also disturb the system. Energy cannot be removed without changing the physical situation. There is no hidden reservoir that refills itself merely because the state continues repeating. In fact, researchers often worry about the system absorbing too much energy from the drive. Heating is one of the threats that can destroy time crystalline order. If energy spreads freely through the many-body system, the sharp temporal pattern eventually disappears. So the real experimental challenge is often preventing unwanted energy absorption, rather than figuring out what to do with unlimited energy coming out. Once that misconception is removed, the scientific value becomes clearer. Time crystals expand our idea of what a phase of matter can be. For a long time, phases were discussed mainly through static properties and equilibrium states. Matter could be solid or liquid, magnetic or non-magnetic, superconducting or ordinary. Time crystals suggest a broader classification in which the dynamics themselves can possess order. This opens a larger landscape of non-equilibrium physics. There may be many phases that exist only because a system is driven. Their defining properties may not be visible in a static photograph. To recognize them, we have to watch how the system evolves. That is a major conceptual shift. Imagine trying to understand music by examining one frozen instant of a vibrating string. Some properties simply exist only in the pattern unfolding through time. Driven quantum matter can be similar. The order is not contained in one snapshot. It is contained in the sequence. Time crystals also remind us that the quantum world becomes especially rich when many particles cooperate. Quantum mechanics is famous for individual oddities such as uncertainty, superposition, and entanglement. But some of the most surprising phenomena appear only when enormous numbers of quantum components interact. Superconductivity is not something one electron does. Magnetism is not explained by one isolated microscopic object. Time crystalline order also belongs to the collective system. This is emergence in one of its clearest forms. The microscopic rules do not contain a tiny label announcing that a time crystal must appear. Individual particles follow quantum mechanics. They interact. They are periodically driven. From those ingredients, a larger pattern emerges that becomes meaningful only at the many-body level. That may ultimately be the most important thing time crystals teach us. The universe can produce forms of organization that are not obvious from the individual pieces. Matter is capable of patterns in more than space. Under the right conditions, the rhythm of change itself can become ordered, and perhaps that is why the name, dramatic as it initially sounds, is actually rather appropriate. A conventional crystal takes the uniform possibility of space and selects a repeating structure. A discrete time crystal takes a repeating temporal drive and selects a larger repeating structure. One creates a lattice of positions. The other creates a lattice in a loose but useful sense of recurring states. Neither requires anything supernatural. Neither makes time stop. Neither allows travel into yesterday. Neither opens a portal. And neither gives you an excuse for being late. What a time crystal gives us instead is a new example of how symmetry can be broken and how collective order can appear. It shows that time translation symmetry, once thought of mainly as a property of the equations describing a system, can become part of the way we classify dynamical phases. It also leaves us with plenty of questions. How many different kinds of time crystalline phases are possible? How long can temporal order survive in increasingly large and realistic systems? What mechanisms can protect it most effectively? Can related ideas be useful in quantum sensing or quantum information processing? What other non-equilibrium phases are waiting to be discovered now that experimentalists can manipulate quantum systems with such extraordinary precision? Those questions are still being explored, and that is probably the healthiest place for a subject like this to be. Time crystals are not a finished story with one neat final definition and nothing left to investigate. They are part of a broader effort to understand quantum matter far from equilibrium. But the central idea no longer needs to feel mysterious. A time crystal is a many-body system that develops robust repeating order in time. In the best-known discrete form, it is periodically driven, yet its collective state repeats with a period larger than that of the drive. This behavior reflects broken discrete time translation symmetry. Interactions help make the response rigid. Special dynamical conditions prevent ordinary heating from immediately destroying it. Everything else grows from that. The crystals in the name refer to order. The time in the name tells us where that order appears, and the strange ticking is not the ticking of a hidden clock, but the repeated return of a collective quantum state. So perhaps the next time you hear the phrase time crystal, you will not picture a glowing gem sitting inside a machine that controls history. You might instead picture a collection of quantum components being nudged again and again, each one interacting with its neighbours until the entire system settles into a rhythm that the external drive did not directly command. A rhythm that remains stable even when the nudges are not perfect. A pattern that exists not because someone arranged a row of atoms through space, but because quantum matter organised the sequence of its own response through time. And after spending so long thinking about that strange rhythm, it seems appropriate to return to a much more ordinary one. Somewhere near you, perhaps there is a clock quietly advancing. Perhaps it is late. Perhaps morning has already arrived. Maybe only a few minutes have passed since you started listening. Or perhaps the whole journey has stretched into that peculiar nighttime space where minutes become difficult to count. So I will ask you once more, just as we did at the beginning, where are you listening from tonight, and what time is it where you are? It is funny that after exploring a form of matter defined by patterns in time, we still return to the little numbers on our screens and clocks. They remain one of the simplest ways we orient ourselves in the world. Yet underneath those familiar seconds lies a universe where time can slow with gravity, where quantum systems can preserve strange memories, and where matter can organise itself into a rhythm that physicists have learned to call crystalline. If you found this quiet journey through the quantum world soothing, interesting, or perhaps just complicated enough to help you forget whatever you were thinking about before bed, I would be very grateful if you liked the video and subscribed to Physics with William. It helps this little corner of calm science reach other curious listeners who might also enjoy taking the long way through some of the universe's stranger ideas. And wherever your own clock happens to be tonight, there is no need to keep perfect time. The quantum particles can take care of the difficult rhythms for a while. You can simply settle back, let the details become a little softer, and leave the time crystals ticking in the laboratory where they belong. Sleep well, fellow traveller, wherever and whenever you are.